चलिए so hopefully I'm live. Hello everyone, very good evening to all of you. How are you all? I hope every one of you is doing absolutely fantastic. This is your chemistry expert Sanjay Arya sir, and today I have come up with a very amazing topic. So since we were continuing our P block in the previous class and we finished group 13 and group 14, today we'll target to finish group 15 to 18. So our target is to finish group 18 up to group 18 from 15. Okay. So guys, let us take a quick recap what we studied in the previous section or previous class. So this is your JEE Main syllabus, which will be mostly appearing in your first attempt of JEE Main. Probably this syllabus will be asked. And because till now we have no as such info related to the course change or the syllabus update of 2025 JEE Main exam, probably the same syllabus will go on. So here we need to discuss group 18 and group 13 to 18. There are total 6 groups in group this entire P block, and here what do we need to study is the general introduction part, that is electronic configuration, their general properties and the trends of physical and chemical properties across the period down the group, and the unique behavior of the first element is usually like carbon has a anomalous properties, nitrogen has anomalous properties in group 15, oxygen has the same in group 16. That is what we have to study. So hopefully we all are ready. Let us start the session now. So guys, group 13 to 14, so group 13 and 14 already covered in last lecture. So here I would go for group 15 to 18 I'll cover. For remaining 4 groups I have to cover. Okay. So let's start the session now. So group 15, what elements are called as group 15? Group 15s guys are also called as nictogens. We call them nictogens. Their hydrides are usually some choking gases, and that is why they called as nictogens. So what nictogens are? Nictogens are these elements: nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. Whatever the trend you use or whatever the mnemonic you use to remember all of these elements is fine, absolutely fine. I usually remember this thing by Nana Patekar, S.A. Bhikhari, kind of. Anyways, so now these all are the elements, and now I'll give you the idea how do we write their electronic configuration so that we can move forward with their other atomic and periodic properties. So let us first come to this part. So nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. So let us first go through their atomic number. You all know that nitrogen has an atomic number of 7. Then their magic number is something that I told you in the previous class also. For all P block, this is what the magic number works. The magic number works like 8, then directly we'll be having 18 because the initial 8 is getting over. 8, 18, 18, 32, 32, like this is how we move. And from first period to second period, the gap was 8, but there is no element as such in the first period of this group, 15th group we call it. So simply 8, 18, 18, 32 and 32. Just remember this part, it is very important. It helps us to find out the electronic configuration, electronic atomic number. 7 plus 8 will become 15, 15 plus 18 will become 33. 33 plus 18 will become 51. 51 plus 32 will be 83. And 83 plus 32 will become 115. This is moscovium. So that is how we find their atomic numbers. First of all, now is the time to write down their electronic configuration. Do remember this part. Their general electronic configuration works in this way. Their general electronic configuration works like NS2 NP, sorry, not like that. So let me just write what I'm teaching you. What is happening here? General electronic configuration. So what is the general electronic configuration of group 15 elements? This is NS2, N-2, F14, N-1, D10 and NP. How many electrons are there? I guess 3. NP3. So it's a half-filled p subshell electronic configuration is there, which is a relatively stable configuration. If we compare this configuration with the group 16 or group 14, this is relatively more stable configuration with half-filled stability or half-filled symmetry we see in the configuration. This is what the configuration we have to use every time. I told you in the previous class also that this is how we can maintain that electronic configuration. Coming over here, nitrogen, talking about nitrogen, second period is here, so we'll write 2s2. So what gas we already have finished in the first period? Noble gas, helium, which has atomic number of 2. So it will become 2s2 and 2p3. Why did we use 2s2, 2p3, not using F and D subshell meanwhile? Because 2 minus F doesn't exist, 2 minus 1D also doesn't exist. Coming to phosphorus, it will become the end of the second period is with neon. Then we have 3s2 and then simply 3p3. Arsenic, this is argon, this is 4s2. Then 4 minus 2F doesn't exist, but 4 minus 1D does. So we will write 3D10, fully filled configuration 3D10. There comes 4P3. Now coming to antimony, the atomic number for antimony, okay, helium, neon, krypton, argon. Then fourth period ends with the gas called as krypton. Krypton, then it will become 5s2. 5 minus 2F, 3F doesn't exist. 5 minus 1D does. So we'll write 4D10 and 5p3. In the similar way, bismuth can go with helium, neon, argon, krypton, xenon, 6s2. Xenon ends with the fifth period, so we'll write 6s2. 6 minus 2f, yes, 4f exists, so we'll write it 4f14. 4 minus 1 is 5d10 and 6p3. Similarly with moscovium, the sixth period ends with, I guess, radon. Helium, neon, argon, krypton, xenon, radon, oganesone. So yes, radon will come. Then comes 7s2. 7 minus 2, yes, 5f14 exists. Then 6d10 will exist. Then 7p3. This is how we write down the electronic configuration. So what is so special in this configuration? What is that thing that keeps on bringing the exceptional behavior to this configuration? First of all is the insertion of D subshell, then another D subshell, then we have F and D, then we have fully filled D and F subshell here, and the same applies over here also. So this is what keeps on bringing the exceptional behaviors. Now let me tell you one more thing, that this 6f14, this 6f14 is called as lanthanides, and this 5f14 is called as the actinides. So guys, this lanthanide will apply lanthanide contraction, actinide will apply actinide contraction. What are these contractions? We already have discussed it, that D and F subshells have poor shielding, and that poor shielding is because of the presence of lesser Z effective, higher, mistakenly went for that. What is was D and F subshells have poor shielding, lesser repulsions because of the higher Z effective. Because D and F subshells are quite bigger in size, they can accommodate more number of electron, and with the addition of an electron, they also add one proton. Their atomic number keeps on increasing, and that is why the effective nuclear charge increases, and that is a property that attracts the electron pair towards the nucleus of the atom, and thus their size decreases. So this is what we call as the lengthened contraction, and similarly it is become actinide contraction. Lengthened and actinide, there are two things, okay? Lengthened contraction, actinide contraction. Let's start with their occurrence. Their occurrence, where do they exist? So coming to nitrogen. So guys, nitrogen, the major source of nitrogen in this atmosphere is the atmospheric gas, which is containing 78% nitrogen by volume. 78% nitrogen is there by volume in the atmosphere. Then we have sodium nitrate NaNO3, which is called as a Chile saltpetre, and this is one of the naturally existing ore of nitrogen, which contains nitrogen in the form of nitrate ion. Another could be the potassium nitrate, called as the Indian saltpetre, where KNO3 has nitrate ion. It's a resource of nitrogen existing on the earth's surface, or sometimes dissolved in the salt form or aqueous solution of the ions in sea water also you may find it, and sometimes in the forms of rock you can find it. Also, there are amino acids and proteins which are called as biomolecules. They also contain nitrogen in them. So that is why plants and animals also contain nitrogen in the form of their proteins and the amino acids. So this is what about the existence of nitrogen. Now let us come to the existence of phosphorus. Where does phosphorus exist? The main source of phosphorus in earth crust is a apatite family that is apatite family, which is an ore of phosphorus, and not just phosphorus. It's a double salt which contain two types of normal salts, such as calcium phosphate and calcium halide. So coming here, just like CA3PO4 whole twice, and we have taken 3 units there. CA3PO4 whole twice, we have taken 3 units there. Dot CaX2. So kind of like mixed salt is here, in which more than one salt is attached via some water of crystallization. So this halogen could be anything. This can be fluorine, chlorine, bromine, and hydroxide also, and according to that its name changes. We are calling it fluoroapatite. Fluoroapatite means calcium fluoride is attached along with your Ca3PO4 whole twice whole 3. So you can also mention this salt as like this, like we all know it is calcium has a +2 charge, phosphate ion will be having -3 charge, cross multiplication this becomes this, and we are taking 3 units of these, and then we are having a calcium hydroxide, calcium halide. And this question has been asked earlier in your JEE exam, so do remember this formula, which is very important formula, the formula of apatite family that has calcium and phosphorus in it with oxygen and halogen. So guys, this is an essential constituent of animal and plant matter, and especially if we talk about our teeth animals are made up of the apatite family. Fluoroapatite only it is made up of, and it is also present in bones as well as in the living cells. And phosphoproteins, the protein which contain phosphorus in them, are actually present in milk and eggs as a major compound. Coming to the arsenic and antimony, they are simply found as the, what is it by the way? Okay, they are mainly found as sulfides. Their traces are found in the earth crust in the form of sulfides. Okay, sulfides. I must write like arsenic has As2S3, Sb2S3 in the oxidation state of +3, right? Then bismuth has Bi2S3, bismuthide, bismuth sulfide, etc. So these are found in in actually traces, found in traces in earth crust, traces in the earth crust. Okay. So that was about the existence of these 15th group element. Now coming to their atomic, or we can call it periodic properties. The very first of them is atomic or ionic radii, which is very simple to explain, guys, because we all know the only variation or the exceptional behavior from the regular one was observed just because of the poor shielding of DNF subshell. That is why only group 13 and 14 suffered for the different anomalous behavior in these properties. Here the trend is absolutely normal. The trend says that nitrogen is smaller in size than phosphorus, then we have sulfur, arsenic, antimony, bismuth, like that. That is how the atomic or ionic size varies, right? This is all about the size. This could be covalent radii, it could be atomic or ionic radii, but if you take about this common radius for all of these, the size or the radius will increase moving down the group very easily. It can be explained, completed. Then we have ionization enthalpy. Ionization enthalpy is something, the property of removal of an electron from the outermost subshell. So as we all know, we are moving down the group, the size increases, that is why the farthest or the most outer electron becomes even farther from the nucleus, which is very easy to remove it out. So we can say that ionization enthalpy keeps on decreasing down the group. So the order becomes nitrogen has the highest ionization enthalpy, followed by phosphorus, then we have arsenic, then we have antimony, and then we have what? Bismuth. So this is the order of first ionization enthalpy, IE1. So in case of any doubt or confusion, do let me know in the comment section or in the doubts section. Next is talking about the electronegativity. Electronegativity is very simpler to write. Electronegativity is something which is a kind of property of a chemically bonded or covalently bonded element that can accept the bonded electron pairs toward itself, and that has been found according to the Pauling scale that fluorine has the highest value of electronegativity as 4. Now coming to other elements, the portion or the part of electronegativity varies like this. Nitrogen has the highest, most electronegative among all of the members of group 15. Nitrogen, phosphorus, arsenic, antimony approximately equals to bismuth. Bismuth and antimony are supposed to have the similar electronegativity value, but rest all of them have higher electronegativities, and we know that nitrogen and phosphorus are typical known metals, and that is why they possess more electronegativity than others. So I don't think there is any doubt in this particular para, talking there some of the periodic properties. Now moving to the next properties, which are physical properties, and I have written all these physical properties together so that we can cover all of them by just once. So all the elements are polyatomic. What is the meaning of polyatomic, everyone? Nitrogen exists as N2, rest all exist as tetra molecule P4, AS4, SB4, Bi4, etc. So what do you observe? That they all exist in the form of tetra molecules. They exist in the terms of tetra molecules. Yes, now another property, their dinitrogen is diatomic, rest others are the tetraatomic, but all of them exist in the terms of polyatomic only. This is the same point only. And nitrogen is the only non-metal which exists as gas. Rest all other P4 exist as solid, then SB4 exists as solid, then Bi4 exists as solid, rest others are solid. Okay, do remember this part. Now coming to their boiling point. Okay, boiling point is what? Boiling point increases down the group because boiling point is directly proportional to the van der Waals force of attraction they are possessing. So van der Waals forces of these are highest in the case of bigger size molecule. So I would simply write that boiling point is directly proportional to the van der Waals forces of attraction, and which is directly proportional to the size. Higher is the size, higher is the van der Waals force of attraction. So what you can easily find that nitrogen has the lowest boiling point and thus it exists as a gas. Rest other have higher boiling point and that is why they exist in their solid state. Now metallic character we talk about, we easily know that nitrogen, phosphorus, arsenic, antimony, bismuth. So guys, we know that nitrogen is a typical non-metal. Nitrogen is a typical non-metal and thus applies with the phosphorus also. These two are actually metalloids. And coming to bismuth, bismuth is a typical metal. So this is how the metallic character varies. Down the group metallic character increases because nitrogen is non-metallic, or phosphorus and nitrogen both are non-metallic in nature. Arsenic and antimony are metalloids and bismuth is typical metal. Now why is it so, by the way? Because of their increase in size and they are due to decrease in the ionization enthalpy. Lower is the ionization enthalpy, it is easy to remove an electron out of that particular atom. If some atom easily loses the electron, it will definitely showing you metallic character in order to acquire the positively charged, that is a cation, formation of a cation. Then we have talking about allotropy. Except nitrogen, all other shows the allotropy. Allotropy is the property of self-linkage. What is allotropy? The property of self-linkage. So I told you in the previous class that carbon has the highest tendency among all the element of self-linkage, and that is why carbon itself has a different branch studied under called as organic chemistry. Rest other like sulfur has the higher allotropy, it forms acid molecules, phosphorus form tetra molecule P4. So apart from all nitrogen is the one that exists into N2 form and doesn't show you allotropy. Rest others show you allotropy and they form tetra molecules where each and every atoms are connected to each other in such a tetrahedral form, and it makes them more stable. Melting and boiling point we talk about, guys. Melting and boiling point both increases down the group. Okay, no, there is an exception I can see. Melting point increases up to arsenic and then up to bismuth it decreases. So more or less we can write it like melting point. If we are talking about melting point, the order varies such as like nitrogen has a lesser melting point than phosphorus, then we have arsenic, then antimony has lesser than arsenic, and this bismuth has the lowest among all except nitrogen. Nitrogen is the lowest. This will become what? Bi4. So what we can see that arsenic will be having the highest melting point in the all process, or is all the comparison of this group. Group 16 element with the highest melting point will be arsenic. And boiling point we already have discussed. So that is what the all physical properties written over there. Everyone have a just look over there. Do remember this part. save a screenshot of this part, because this is gonna to be used various times by us in so many questions which we are gonna to face right now from here. So there we start from the very first question from here. The very first question over here is, nitrogen is an essential constituent of what? Fats and carbohydrates? No. Carbohydrates and fat contains mostly carbon, hydrogen and oxygen. Proteins and amino acid? Yes, all the amino acids have this type of structure where one of the group is COH, another group is NH2. So thus, yes, amino acids and proteins have this. Concentrated H2SO4 and Na2O2. I don't know what is it talking about, but it will be definitely forming hydrogen peroxide, and so there is no nitrogen, I see, so this will be cancelled out. Vitamin A and vitamin B are also not a source of nitrogen. The only correct answer should be what? B. All well, all set, all cool. So keep on liking the session, everyone. Those who haven't liked the session, do like the session. Next is, which of the following element does not show allotropy? So we all know that nitrogen is the only element that exists as N2, and rest all of them exist as P4, AS4, SB4 or Bi form. So the only answer is nitrogen. So allotropy is the property of self-linkage. See, these four are self-linked to each other like this. I guess that was an easy question. Now moving forward, we have another question. Not another question. We have chemical properties. So this is how we'll go in the every chapter, because there were initially, the chapter was a quite huge chapter. There was a lot of things to cover in this chapter. And probably this chapter used to take so many time because we used to discuss about the compounds of these elements which we see here. Compounds of group 15, 16, 17 like that. And there were a lot of number of compounds which we used to study, like nitrogen. If you talk about, there are a lot of nitrogen itself, N2 dinitrogen we had to study. Then we used to study ammonia as a very important gas. And then apart from ammonia, nitrogen oxides were there. Nitric oxide, nitrogen dioxide, N2O3, N2O5, N2O4, okay. And then we used to study nitric acid, HNO3. So in the similar way, sulfur will come to 16th group, will reach to sulfur, sulfuric acid and sulfur dioxide, trioxides. So there were a lot of things that was initially included in your syllabus. As we all know that in JEE Main, these things have been removed. The only properties that are asked are the physical, chemical and periodic properties and their electronic configurations. Then like these are the something which we have to study. So as of now, taking JEE Main and the priority note, we are ignoring the other parts, other things such as the properties of the compound involved. But yes, the moment we will be studying for JEE Advanced right after our JEE Main first exam, we will surely come with those topics also which I have right now eliminated as per the like guidance of JEE Main. Okay, so what we are covering is the one which is asked, which is going to be asked in our JEE 25 exam. Mains. Oxidation state, let us discuss about the oxidation state, everyone. What oxidation states are exactly? Whenever they form compounds, so what kind of like partial or fully charged can they exhibit? Taking nitrogen into account, it shows you -3 to +5. And let me just give you this example that will give you a more clarity over this topic. Take this example over here. NH3 is one compound. N2H4 hydrazine is one compound. N2 is something. Then we have nitrous oxide, nitric oxide, dinitrogen trioxide, nitrogen dioxide, N2O4, and then we also have N2O5. These are some compounds of nitrogen that exist in nature. We all are very well aware of these compounds. So if you find the oxidation state, guys, it's very easy to find out. Take X as the oxidation state of nitrogen. Hydrogen has +1, so X becomes -3. So this is having -3 oxidation state. In the similar way, you can identify this for everyone. This will become -2. This will become 0. this will become positive 1, we call it as nitrous oxide. This is positive 2, we call it nitric oxide, dinitrogen trioxide, nitrogen dioxide, brown color gas. Then this is also positive 4, dinitrogen tetraoxide, a dimer of NO2, and N2O5 is dinitrogen pentoxide, which is present in positive 5 oxidation state. So take everything into account. So that is how we calculate their oxidation states, and there could be variable oxidation state for all of these elements. Now talking about only nitrogen, nitrogen has an oxidation state ranging from -3 to positive 5 under such compounds. Very well clear, very good. And these are the most common oxidation state are -3, positive this 3 and this, and I can give you these examples also, just like NH3. Positive would be NF3 and N2O5. Check out their oxidation state is -3, positive 3 and positive 5. The same applies with phosphorus, also has the similar oxidation states. Same applies with these. Only bismuth is there that shows positive 3 or not positive 5. Why doesn't it show not shows oxidation state is equals to positive 5? Why is it so? The reason is due to inert pair effect. This is all because of the inert pair effect. What is inert pair effect? I already have explained this thing into our previous class. What I explained was, then whenever we go down the group, moving down the group with the addition of D and F subshell, the what we can call it poor shielding of D and F subshell works, where we can say that Z effective decreases, and due to which, increases, Z effective increases because poor shielding is there. Because of this reason, what happens actually, nucleus is very much closer, or we can say the NS orbitals are NS, which is a spherical orbital, and let us just talk about arsenic if I say. So this NS orbitals are very closer to the nucleus, and that is why they kindly become inert. They do not participate in bonding, and only NP3 orbitals participate in bonding. That's why we call it inert pair effect. Okay, let me just give you an idea about inert pair effect, or you can take this idea like this. So nitrogen, phosphorus, arsenic, antimony, bismuth. Their atomic numbers 7, 15 plus 18, 33 plus 33 plus 18, 51, and then add one more 32 here. So 32 here will become 83. So their electronic configurations, we all know that this was helium and 2s2, 2p3. This is phosphorus, which is neon, 3s2, 3p3. So we have argon, 4s2, 3d10, 4p3, krypton, xenon. Now check it out. With this addition of this, we call it lanthanides, and lanthanide causes lanthanide contraction, and also this D and F subshells have what? Poor shielding. They show poor shielding. And now if they are showing poor shielding, this NS electron what we are talking about is, where are the NS electron? This one, this one, this one. So this all these electron pair gets closer, this electron pair gets closer to nucleus. Because they are very close to the nucleus, they become inert, doesn't participate in bonding. And that is why, guys, I keep on saying that oxidation state, if we talk about the oxidation state, so exactly like oxidation state, from positive 3, oxidation state increases down the group, like positive 3 stability I am talking about. Stability of positive 3 oxidation state. But if we talk about the same for, so for positive 5 oxidation state, and that too we are talking about this stability moving down the group, decreases down the group, like that. Let's say if I ask you that which is more stable, NCl3, PCl3, ASCl3, SbCl3, BiCl3. So the correct answer will be, this is the order of stability. What about this question? Let's say if I talk about the PCl5, ASCl5, SbCl5 or BiCl5. So BiCl5 doesn't exist, everyone, because of the inert pair effect. It doesn't show you positive 5 oxidation state. This is the order of stability. You can also write down their oxidation state if you want. Here everyone is having positive 5 oxidation state. Here it was positive 3 everywhere. That is what the variation of oxidation state is. And how does it work? It works on the basis of the inert pair effect. This inert pair effect keeps on decreasing the oxidation state by going there down the group. And usually this decrement is of unit 2 because there are n s2 electron which becomes very close to the nucleus and they become inert. That's how we define them. Fine. Now, some special properties or feature we will know about group 15 and their oxidation state, such as talking about nitrogen. Nitrogen usually has positive 3, minus 3 and positive 5 oxidation states. But always remember that if any oxidation state is there, that is from minus 1 to positive 4. This is a very important property I am explaining you. Every such acid or every such basically a compound dissociates into higher and lower oxidation states, and such type of reactions are called as disproportionation reaction. Now, what is the meaning of disproportionation reaction? A reaction in which the same element of a compound can undergo oxidation and reduction. Take this example in the account. HNO2 has a positive 3 oxidation state. Nitrous acid, nitric acid has positive 5 and nitric oxide has positive 2. So what we can see that something is going from positive 3 to positive 2 is a part called as reduction, and if something is undergoing positive 3 to positive 5, this is called as oxidation. So if the same element of a compound can undergo oxidation and reduction simultaneously together, such type of reactions are called as disproportionation reaction. And remember, all the acids which are generally having +1 or +1 to 4 oxidation state, they will undergo disproportionation in their aqueous solution. First property. Number 2 property, the maximum covalency of nitrogen is 4 because of the unavailability of d orbitals. So guys, always remember this thing, that if we talk about the any of the element belonging to second period, any element, whatever be, carbon, boron, nitrogen, oxygen, fluorine, any of the element that belongs to the second period will definitely be having maximum covalency up to 4. It cannot extend its covalency. Why is it so? Because second period element have only 2 type of atomic orbitals, 2 type as in one subshell is S, another is P. So 2s it has only 1 orbital, 2p it has 3 orbital. In total there are 4 atomic orbitals available. So maximum number of electrons it can accommodate is 8, and maximum number of covalent bond it can form is 4, because one covalent bond is formed by 2 electron. And that's why all the elements belonging to second period can have maximum covalency of just 4. But right after that, if we start it from the third period or beyond we go, then they can accommodate more number of electrons, because they have 3s, 3p and 3d orbital. These empty 3d orbital can have this benefit of making even number of bonds more than 4, such as PCl5 exists, NCl5 doesn't. That's what I'm talking about. So whoever is facing any problem, you can write down your doubts in this comment section. Like Sai Shivani is mentioning one problem. She didn't do her 11th standard well. Can she complete her 12th standard from here? So this channel is an ideal channel for every one of you or such kind of student which are facing the problems related to your notes or the coverage of the syllabus. This is something where this is the channel where we are providing you everything as in your complete 11th standard syllabus will be covered this year, your complete 12th standard syllabus will be covered this year, and right after finishing of the remaining some of the chapters which are inorganic chemistry chapter, I have already completed all the chapters from physical chemistry, whether it is 11th standard or 12th standard. Right after that, I'll finish complete your inorganic chemistry, and after inorganic chemistry, you will be having only one segment, that is organic chemistry. We'll finish the organic chemistry, and that all will be happening right before till your examination. So just subscribe to the channel, everyone. Stay here, be patient, download the notes from our Telegram channel. The link is given there in the comment, and keep your practicing going on like this. Now we have phosphorus. If we talk about, we are talking about the phosphorus. So phosphorus, nearly all the intermediate oxidation states, they disproportionate into +5 and -3 in the alkali and acid, both of the medium. Take this example, very important reaction, that phosphorus in 0 oxidation state on reaction with sodium hydroxide disproportionates itself and produces a compound called phosphine pH3 plus NaH2 PO2, NaH2 PO2. Give me a sec here. So guys, here phosphorus is in the oxidation state. Take this example I told you. This is an example of the disproportionation reaction of phosphorus showing in the intermediate oxidation state, and especially its acidic condition. or like basic condition, sometimes it happens. Phosphorus is in zero oxidation state. So zero oxidation state is here. Phosphorus here has -3 oxidation state. Here it has +1 oxidation state. And if you balance this equation, you need to apply 3 over here. Now it is a balanced chemical equation. And rest you can add water if you want to balance this equation. The rest of the things we can add water. Like 6 are here, 3 are here. So you can add 3H2O here. Now this is a balanced chemical equation. Right. So this is a disproportionation reaction of phosphorus, which you can see. Now coming to the next point is that oxidation state of +3 in the case of arsenic antimony becomes more stable because of the inert pair effect, and it is stable with respect to the disproportionation. It doesn't undergo disproportionation. Positive oxidation state in the case of these are becomes more stable. And if we talk about the heavier element, because of their presence of vacant d orbital, the outermost shell, which can be used for the bonding, they can expand their covalency beyond 4. Like nitrogen can only give it the covalency maximum up to 4, but these can show even beyond that. And we all know the examples. PCl5 exists, NCl5 doesn't, right? Keep on liking the session. Those whoever are watching me, do like the session, everyone. Yes, it is very mandatory. World Explore Wild is with us. He is asking, is it necessary to study 11th class organic chemistry, or can we directly start 12th class? No, you cannot start direct 12th class chemistry. Before that, you need to study at least reaction mechanism part. GOC is very much important to cover, otherwise you will not be able to like understand complete 12th standard organic chemistry, because majority of organic chemistry is in your 12th standard only. 11th standard only contains 2 chapters, GOC and hydrocarbon. Do remember that part, do cover that part, and we'll come to that part also. I'll write after this, I'll start GOC, so you will come to know, and I will give you the complete chapter completion, so you can even prepare from here also. Now we have reactivity with hydrogen. We all know usually they form trihydride. Trihydride is in NH3, PH3, and there I'll explain very good point out of that. So if you talk about all the group 15 can form their hydrides in the formula of NMH3, and with a triangular pyramidal shape, the hydrides show regular degradation in their properties. Okay, talking about thermal stability. So guys, NH3 is the most stable. Then we have PH3, relatively lesser stable. Then we have ASH3, and then we have, let me first write their names, guys. NH3 we all know is called as ammonia gas or ammonia. Then we have PH3 called as phosphine, one of the toxic gas. Then we have ASH3, SBH3, BH3. You might be wondering, why am I not considering moscovium right? Moscovium it's a man-made element, and it's a radioactive element, and we don't study too much properties of such radioactive elements, and these are the only element that we have to study. Okay, this is called as arsine, this is called as stebine, this is called as bismuthine. So that is what they are named up to. Okay, usually they form trihydrides. If we talk about their thermal stability or their reducing character, these two are inversely proportional to each other. Let us say, take these examples, that NH3, PH3, ASH3, SBH3 and BiH3. So you will find that this bond between nitrogen and hydrogen, this is your 2p and 1s bond, this is your 3p and 1s bond, this is 4p and 1s bond, this is 5p and 1s bond, and this is 6p and 1s bond. And we all know, sir, 6p cannot overlap with 1s orbital very easily, and that's why their stability of these bond and the molecule becomes this. This is the order of their thermal stability. The stability order is somehow like this. But now what if we talk about their reducing characteristic? So reducing character of hydride is inversely proportional to the bond energy of metal hydrogen bond. So easy, you can dissociate the bond and their reducing character will increase, availability of hydrogen will increase, and thus guys the order will become what? NH3, then PH3, then arsine, then stebine, and then we have bismuthine. So their order will become oppositely as a reducing character, as a reducing nature or a reducing agent. Strength of reducing agent increases moving down the group because of the availability of easily produced hydrogen for the reduction process. Hopefully this part is very much clear to all of you. This is very important, from where so many questions have been asked previously, and believe me, similar questions will be asked in your JEE Main 2025 exam also. Do remember this point, very important part I have covered here. So now we have their boiling point and melting point. If we talk about everyone, because nitrogen contains the hydrogen bonding, the melting and boiling point will be highest in the case of nitrogen hydride, rest it will decrease. See, talking about boiling point will be increasing, right? We can say that coming from here to here, the boiling point increases, and because size also increases, right everyone? I told you once that boiling point is directly proportional to the van der Waals forces of attraction, and which is also directly proportional. Boiling point is directly proportional to this, and this is also proportional to the size. So with the increase in size, their attraction increases. As the attraction increases, their boiling point also increases. Now talking about the melting point is also something like that, keeps on increasing. Now talking from here to here we are going, so melting point also increases, but this is exceptional. Nitrogen hydrides at the exceptional, and let me just explain this part. Note, both melting and boiling point are the highest for NH3 compared to other hydrides because of, why is it so? Because of hydrogen bonding existing in ammonia. So guys, wherever the hydrogen bonding occurs, this hydrogen bonding keeps the molecules closer to each other and bonded to each other and doesn't let the molecule dissociate. Take this example, everyone. Let us say we are talking about NH3, we are talking about. So this is how it looks like. Some another nitrogen will be having bond over here, some another will be having over here. So this is how it works and so on. So it's a huge chain can be formed of this nitrogen. And this kind of bonding, hydrogen bonding, is absent in the case of other hydride. So others we do not need to take into account. We can easily ignore the others. What else is there? Yes, I think all the properties have been covered till here. Then we have basic nature. If we talk about which one of them has the higher basic nature. So guys, basic nature follows the order of this NH3, PH3, SBH3 and then this. This is the order of their basic strength or Kb. Basic strength is highest for the nitrogen NH3. So why is it so, by the way? So if we talk about the NH3 versus BF3, boron trifluoride, this is how their bond is formed. This NH3 works as a lone pair donor. So it works as Lewis base, and this is your lone pair acceptor and called as Lewis acid. I remember in the previous class I taught you about the same concept of lone pair donor acceptor, where BF3 was the what should I call it, lowest acidic Lewis acid comparing to BCl3, BR3, BI3. BI3 was the highest because of the because in BF3 maximum extent of back bonding occurs. BI3 is the least amount of back bonding occurs. That's why that make it accept the electron pair from the ammonia, and ammonia is working as a Lewis base here. So another thing is, what we can simply conclude is that the basic strength, so Lewis basic strength of a base is directly proportional to the electron density. Higher is the electron density, higher is the chance to donate the electron pair to somewhere. And if we talk about the same in the period, in the group, size matters, along the period electronegativity matters. So what do we see? That NH3, PH3, ASH3, SBH3, BIH3. This is what the order of Kb, which is directly proportional to what? Electron density. So electron density is highest in the case of NH3, and that's why NH3 is assumed to be the most basic among all of the given compounds. I hope this part is very much clear to all of you. I have explained it very well. Next is the reactivity. If we talk about, well, everything can be easily understandable. because I already have explained this part that melting and boiling point are exceptionally higher. Melting and boiling points are exceptionally higher for these two due to H bonding, and rest it increases down the group due to H bonding. For rest of the cases it increases down the group because of the size increases and van der Waals force of attraction increases, which you can see from coming left to the right like this. It keeps on increasing, both of the things, boiling and melting point. Bond energy will definitely decrease. Moving down the group. You can check it out, metal and hydrogen bond, it is going what? It keeps on what? Decreases. Why does it decreases? I already have given you the perfect explanation, because the bond is 1s and 2p here. This bond is 1s and 3p. This is 1s and 4p, 1s and 5p, and 1s and 6p. And that's why the bond energy decreases down the group. You can check it out, this value. This is also this is what the enthalpy of formation. Higher is the negative enthalpy of formation, lower is the, we can say more is the stability of, so thermal stability will be higher, right? Thermal stability is directly proportional to the more negative enthalpy of formation. So most thermal stability is ammonia and least thermally stable is BiH3. It dissociates easily. So in between these, I will give you one more bestest example to explain you the Drago's hypothesis. Meanwhile, although this is a part of chemical bonding, and I already have explained in chemical bonding also, but let me give you a brief about this, that if we talk about the NH3, PH3, ASH3, SBH3, BiH3. So let us just consider this part. We all know all the hydrides, they have some shape or the geometry somehow like this, that nitrogen is there. This is a one lone pair, one hydrogen and another hydrogen. Let us say this is coming out of the plane, and this is going inside the plane. This is how the structure look like. So guys, if you measure either of the angle, so we can simply write that the hybridization of nitrogen or any central atom will be sp3. The geometry is, for sp3 hybridization, geometry will always be tetrahedral. The shape, if we talk about, will always be called as pyramidal. So we call it trigonal pyramidal. Now talking about the bond angle. Bond angle is nearly 109 degree 28 minute, which is lesser than that 109 degree 28 minute because of the due to lone pair bond pair repulsion. This lone pair bond pair repulsion will lead to this theta. This is your LP BP repulsion. Lone pair and bond pair repulsion leads to decrease in the bond angle directly from, this is the perfect example here, in carbon methane molecule, if we talk about methane molecule, guys, the theta between carbon, hydrogen and hydrogen is 109 degree 28 minute. If we are going for ammonia, where one lone pair hydrogen, this is there, the theta over here will be 107 degree nearly. And for water, this bond angle is very lesser, nearly 104.5 degree. So this is what I want to tell you guys, that hybridization is a factor that decides the bond angle, but apart from hybridization there are so many other factors which are the repulsions caused by lone pair and bond pair. Here lone pair bond pair repulsion is there, here lone pair repulsion is there. Here it was no as such repulsion, that's why the exact bond angle is 109 degree 28 minute. But the problem arises where we talk about the rest of the members. You will not believe me, but the bond angle of we are talking about same hydrogen E HEH bond angle. So this HEH bond angle is 107.5 degree in the case of ammonia. In case of pH3, this is 91.5 degree. It is 91 degree. It is around 90.5 degree, and this is only 90 degree. The question is why? The question is why is it so much depressed in the angle, like so bond angle decreases, we all know bond angle decreases, but why abruptly, इतना भयंकर तरीके से, like why abruptly the bond angle has decreased, right? From here to here bond angle has decreased so much. So the one reason that is very much explainable is, talking about nitrogen, we all know that shared pair of electron will be nearly closer to nitrogen, because nitrogen is more electronegative. Nitrogen is what? More electronegative, and thus it is causing more repulsion, and theta is directly proportional to the electronic repulsion. Higher is the electronic repulsion, higher is the magnitude of angle. But if we talk about why is it so good, because nitrogen is more electronegative. The same thing if you talk about bismuth, the electron pair will shift it to somehow like this. So we can say lesser repulsion is there if the electron pairs are closer to the central atom. If electron pairs will be closer to the central atom, higher will be the repulsion, and since there is lesser repulsion, BiS3 is a lesser bond angle. Lesser repulsion, higher is the repulsion, lesser is the bond angle. So theta is actually inversely proportional to the electronic repulsion. Higher is electronic repulsion, smaller is bond angle. theta. So that is what it happens. Okay, this is one reason, but the another question comes कि why abruptly is it happening? Abruptly as in like it has dropped from 107 to somewhere. So guys, the actual reason behind is Drago's hypothesis or Drago's rule, we call it. Using this Drago's hypothesis, this is very easy to explain, that no hybridization occurs in hydrides of third period or higher. Third period or higher will have no hybridization. So since there is no hybridization, everyone, what do you understand from here? Talking about nitrogen, the hybridization over here is sp3. sp3 and bond angle should be 109 degree 28 minute, but actually 107.5 degree due to lone pair bond pair repulsion. Because of the repulsion, the bond angle has reduced here. It is very much explainable. But talking about phosphorus or rest of the other member, they are somehow like this, right? Why is it so? Because for phosphorus, this is your 3s orbital, 3s2, and 3p1, this is your 3p. So this is your px, let's say. So this is px, py and pz. 90 degree bond angle, right? So basically there is no hybridization, only 3 pure p orbitals overlap with 3 1s orbitals of 3 hydrogen atoms. So since there is no hybridization occurring, the angle between x, y, z axis will be 90 degree, and that is what it has been followed for all. Let it be nearly 90 degree angle will be observed. This is what we call as, this is something that we call as the Drago's hypothesis. And believe me, not just over here, the Drago's hypothesis especially works in the cases of metal hydrides or element hydrides, and those hydrides which are having at least 1 or 2 lone pairs in them. So let me just clarify one more thing where you can observe this Drago's hypothesis. Drago's hypothesis is observed in hydrides only. Hydrides only. Hydrides only with hybridization no tetrahedral, no like that we can write it, with steric number is equals to 4, steric number means bond pair plus lone pair on central atom. Minimum number of lone pair, or we can write okay, allow me a second, allow me a moment. वो अपने आप ही गायब हो गया सब कुछ, क्या हुआ है बोर्ड पे पता नहीं। हाँ लेकिन क्यों हुआ भाई, ये तो मैंने कुछ किया भी नहीं था। एक सेकेंड अभी चेक कर रहा हूँ, पीछे से भी सही था। हाँ रेड अपने आप हो गई थी, ब्लू से रेड हो गई थी, और आवाज़ कंटिन्यूसली आ रही थी कुछ स्पार्क होने की। कोई नहीं, अब तो मैंने चालू तो कर दिया है इसको, बट सब खराब हो गया। वो वापस से इंपोर्ट करना पड़ेगा हमें, और वो सेव भी नहीं हुआ होगा। नहीं खुलेगा यार, क्योंकि वो लैपटॉप रीस्टार्ट हो गया ना पूरा। यार क्या है ये फ़ोन यार, पीछे लटक रहा था। अच्छा अच्छा अच्छा, और मैं आपसे बोलने वाला था उस समय, दो बातें डिस्कस करनी थी। एक तो ये आवाज़ें आ रही थी। अच्छा अच्छा, उसको रिकवर कर सकते हैं? कुछ भी तो नहीं है, तो नया पेज खुला हुआ है। किस पर? नेम्ड? नो नो ऐसा नहीं है, वो तो दिस फॉलोइंग डॉक्यूमेंट इज नॉट क्लोज नॉर्मली। नहीं वैसा खुल जाएगा, यही खुलेगा। खुलेगा? रिमाइंड मी नेक्स्ट, एक बार आगे पीछे करो। अरे नहीं है, आगे करना एक बार साइड, बस वही है। और लिखा हुआ भी है इसमें। चलो थैंक यू सर। So guys, there was some little interruption we faced. Hopefully everything is fine now. As you all can see, automatically things got off, and thankfully nothing is harmed here. So anyways, in very detail we were discussing about the यार क्या हो रहा है ये। We reached to the Drago's hypothesis, and I was telling where you can apply the Drago's hypothesis. So now let's see where can we apply Drago hypothesis. Okay, so Drago's hypothesis can be applied to metal hydrides only, and at least one lone pair on central atom, and central atom must belong to third period or higher. It is applicable only up to hydrides only with steric number What is the meaning of steric number? Steric number means bond pair plus lone pair is equals to 4. So that is the condition. So guys, everywhere you can observe the same, but next time it will come, I will simply write Drago's hypothesis. The only hydrides are 15th group that face the Drago's hypothesis, 15th group hydrides, and the 16th group hydride. So 15th group hydrides are ammonia, phosphine, arsine, stebine, bismuthine, and 16th group are water, hydrogen sulfide, hydrogen selenide, telluride, polonide, जो भी है ऐसा, like that. So there you will find the bond angles as per the Drago hypothesis. The bond angle in ammonia is 107.5 degree. Phosphine, the bond angle is 0.5 and 91.5 degree, nearby to this, 91 degree, then 90.5 degree and nearly 90 degree. Here also the variation is like 104.5 degree, then around 91, 92 degree or 91.5 degree, 91 degree, 90 degree nearly. This is how the variation works. These are not the exact values. These values are only to give you the idea that how does Drago's hypothesis works. So finally, now we will be moving forward from this topic of hydrides. We have reactivity with oxygen. So guys, usually they show positive 2 and positive 3 and positive 5 oxidation states in common. So oxygen, if we talk about the reactivity, oxygen will give you compounds like this, like N2O3, P2O3, AS2O3, Sb2O3 in positive 3 oxidation state. So there could be possibly two type of oxides they form, positive 2 and positive 5. Talking about the positive 3 oxides, we have nitric oxide and dinitrogen trioxide, diphosphorus trioxide. These all are acidic in nature. These AS2O3 and Sb2S3 are amphoteric in nature, and Bi2O3 being the metallic oxide is purely basic in nature. Bismuth doesn't form Bi2O5 because in positive 5 oxidation state bismuth doesn't exist very well because of the inert pair effect. Rest all can form you M2O5 kind of oxide, and all of them are acidic in nature. All of them are acidic in nature. Next we have reactivity with halogen. So guys, if we talk about their halides, there are usually two type of halides, NCl3 and NCl5. Like we can write it like PCl3 and PCl5. Examples. So nitrogen doesn't form pentahalide because of the non-availability of d orbital, or we can simply say it can extend, it can have the maximum covalency up to 4 only, cannot extend beyond that. Then all the trihalides of these except those of the nitrogen are stable, and nitrogen is only stable for NF3. The only stable halide of nitrogen is in trihalide is NF3. And why does it other exist? Let me tell you, due to smaller size, of nitrogen can't accommodate 3 large sized halogen atoms, but others can. Nitrogen cannot accept, or nitrogen cannot have a preparation or like availability with accommodate 3 large sized pairs, 3 large sized atoms. Rest all do. Okay. Talking about the covalent character is directly proportional to the polarization, or polarization is directly proportional to the positive charge present on the central atom. So central atom with positive 5 oxidation state will be having higher covalent charge than positive 3 oxidation state. And let me just write it. This is explained by, this has already been explained by me and under explained by Fajan's rule. We have already covered this part in covalent bonding, so I will not go for this part again, but it is explained very well by Fajan's rule, that polarizing nature, or we can call it the polarizability. There are two things, and higher is the polarization, higher is the covalent character in that compound. So covalent character is directly proportional to the polarizing ability of an ion, and polarizing ability an ion is directly proportional to the size. Higher is the size, higher is the charge on that anion, it will be having higher polarizability. And talking about the polarizing power of a cation, higher is the charge, smaller is the size, higher will be its polarizing power. So polarizing power will be higher in the case of element containing positive 5 oxidation state rather than positive 3 oxidation state. So that is how it is defined. Then we have reactivity with metals. So usually they all form the compounds with metal in their tri state with -3 oxidation state. You can check it out. Talking about calcium nitride, so who reacts directly with these elements forming these compound? These all elements react with metal to form their binary compounds exhibiting -3 oxidation state, and -3 is like calcium is in positive oxidation state, this is -3. Then we have calcium also over here, plus calcium has a positive 2 oxidation state, -3 for phosphide, +1, -3, +2, -3, +2, -3. So this is how you can define and you can calculate it out. It's a very simple basic concept that we use in redox reaction. Hopefully this part is absolutely clear to all of you. Moving forward, now we'll be solving some questions about the chemical properties we studied for all group 15 element, and then we'll come to group 16. Thereafter we'll be having a short break, and then we'll join you back with completion of group 17 and 18. So today our target is to complete all the 4 groups. Start with this question: which of the following is the increasing order of enthalpy of vaporization? What do you think? Which of them will be having increasing enthalpy of vaporization? So guys, enthalpy of vaporization, delta H of vaporization is directly proportional to the boiling point or directly proportional to the van der Waals force of attraction, intermolecular attraction, I must write. This is directly proportional to the intermolecular attraction. So we all know that nitrogen, ammonia has highest because of due to H bonding. But talking to pH3, it has lesser than ASH3 because the size increases. As per the size increases, their van der Waals force of attraction increases. So they're increasing, the boiling point increases, and boiling point is the highest for ammonia. Correct answer should be enthalpy in increasing order. NH3 should be at last, then D is the correct answer. Check it out, everyone, check it out. D is the correct answer. Next question. What do you think? Which of them is amphoteric in nature? Very easy question. The one which we recently discovered and identified. We recently discussed about this. Which of the following is amphoteric in nature? So amphoteric nature can be explained using talking about all the oxides, N2O3, then we have P2O3, then we have AS2O3, Sb2O3 and bismuth oxide Bi2O3. If we talk about their acidic and basic behavior, both of the typical non-metallic oxides are acidic in nature. Both of the metalloid oxides are amphoteric in nature. And now the last one is basic in nature because it's a typical metallic oxide. Clear, everyone? Hopefully this part is absolutely clear now. So what will be the correct answer? Which of the following are amphoteric? Antimony oxide, Sb2O3. Satyendra Kumar, just check it out. N2O3A is the incorrect answer because that is an acidic oxide. Next question. What about the basic strength of the hydrides of group 15? What do you think? Basic strength. If we are talking about basic strength means we are talking them as a Lewis base. And this is directly proportional to the electron density present on the atom. Especially we are talking down the group. If we are going down the group, we need to consider the if we are talking about their Lewis base strength, we have to talk about their electron density. And moving down the group, we have to basically think of their size. Higher is the size, lesser is the electron density. Smaller is the size, higher will be the electron density. The correct answer will become, it increases or decreases? Decreases down the group, very simple. A should be the correct answer. And let me write the order also. Basicity if we talk about, or the basic strength we talk about, ammonia is most basic. Then we have PH3, ASH3, SBH3 and BIH3. This is the order of basic strength. Next question, try the next question. You people, rest of the people try this question and let me take this doubt. How to manage +2? I am only focusing on entrance. Well, your +2 exam will automatically be what can I say, managed. If you are preparing for JEE or similar difficulty level kind of examination, then definitely after a while you can easily cover your board's exam or 12th standard also. Okay, the very first thing that you need to do is to focus only on the JEE Main first attempt, because that will give you the clarity where do you exactly stand. Right after that, you have plenty of time to prepare for your school examinations and especially the board exam you will be facing. There is a question. Elements of group 15 compounds in positive 5 oxidation state. However, bismuth only forms a well characterized compound of positive 5. What is that compound? So guys, do remember this part. The only compound of bismuth in its positive 5 oxidation state is BiF5. The only compound that exists as positive 5 oxidation state is BiF5. Rest other exist in the positive 3 oxidation state only. Let's try another question from here, everyone. Let's try another question. There we go. Everybody please try this question. Which of the following is trihalide is unstable? The only trihalides which are unstable are the trihalides of nitrogen. The only known hydride of hydrogen nitrogen that exists is NF3. So NCl3 is the correct answer. NCl3 is an explosive and unstable. It's not stable actually. Now, anomalous behavior of the first member of every group is nitrogen. Nitrogen in the nitrogen family is the first member, and because of its small size and its higher electronegativity, also unavailability of d orbitals, it doesn't form 5 bonds, it does not expand its electronegativity beyond 5. Okay, read it out, everyone, read it out. Allow me a moment. So yes everyone, now we are continuing from here. So what I'm saying is that nitrogen shows anomalous behavior, exceptional behavior from the rest of the members of 15th group. And why is it so? Because of its smaller size, its high electronegativity, high ionization enthalpy, and mostly its absence of d orbital. D orbitals aren't there, that's why the maximum covalency it can show is 4. Rest of the other member can show covalency beyond that, just like PCl5 has covalency of 5, but nitrogen, it has only covalency of maximum of 4, NH4 positive ion, like that. Now coming to nitrogen, it has a unique ability to form the pp bonding. So guys, always remember, wherever you can find the like whoever can form the extent of pi bonding, like who forms the pi bonding, which elements can form the pi bonding, it is inversely proportional to the property of the size. Bigger is the size, lesser is the lateral overlapping extent, and that's why nitrogen is the only element that can form pi bonding. Size increases, pi bonding will decrease down. But however, the nitrogen-nitrogen bond is weaker than the other bonds because of the high electronic repulsion, small length. So guys, this is what we are talking about, nitrogen-nitrogen single bond we are talking about, not about the triple bond we are talking about. We are talking about this single bond only, nitrogen, because as we all know that there is a small size, and this will having high repulsion. Here we can see higher repulsion, which will not be seen in the case of phosphorus, because phosphorus being bigger in size, they will be separated by a larger distance, and due to which there is a kind of like smaller repulsion or lesser repulsion, we can say. There is a lesser repulsion between these two phosphorus atom, and there again we are talking about the single bond. But if we talk about the nitrogen-nitrogen triple bond, if we talk about the nitrogen-nitrogen triple bond, this is the strongest bond of existing elements. Thus N2 gas acts as an inert gas. It acts as an inert gas. Thus nitrogen acts as an inert gas. So these are very important point to remember. And as a result, nitrogen has a poor catenation tendency. Why is it having a poor tendency of catenation? Because the nitrogen-nitrogen single bonds are not stable. Nitrogen-nitrogen multiple bond, that is triple bond, is highly stable because of the extent of what we can say pp bonding, which is a pi bonding. Pi and sigma both are taking place in the case of N2. That is why N2 molecule is very stable. What about the NN bond? NN single bond are not stable as PP, AS, ASAS and SB, because they are having larger size, lesser electronic repulsion. Nitrogen has a higher repulsion between two nitrogen atoms. That's why nitrogen cannot form a single bond. Now we will be having another. Nitrogen forms N2, but phosphorus does not form P2. However, it converts for P4. Why is it so? Because it's very easy that phosphorus can't make pi bonds, very first. Number 2, NN single bond doesn't exist, is unstable, PP single bond exists and thus forms P4 molecule. That is why it formed what? P4 molecule. Remember these points. So a triple bond is present between phosphorus atom. Absolutely incorrect. Why? Because there is no there is no pi bonding can exist between two phosphorus atom. P-pi bonding is weak. True. P-pi is strong. If it would have been strong, definitely there would be a phosphorus multiple bond. And multiple bond form easily? No, it is not form easily. That's why phosphorus doesn't exist as a P2 molecule. It only exists as P4 molecule. Correct answer B. Next question. We have another question here, everyone. Which of the following has the lowest boiling point? As I told you that boiling point in ammonia is exceptionally higher because of due to H bonding, due to interparticle stronger bonding, due to hydrogen bonding. Ammonia has the highest boiling point among all of the existing species, even for pH 3, but rest of the species will be having higher boiling point because of their larger size. Higher is the size, higher is the van der Waals force of attraction, higher will be the boiling point. pH3, ASH3, SBH3, BiH3. This is the order of boiling point. So our question was the lowest boiling point. Now can you identify the element with the lowest boiling point? So yes, this is the one with the lowest boiling point and lowest interparticle forces of attraction. The correct answer should be B. How good is this question, man? This question can be easily asked in JEE Main 2025. We all know the updated syllabus till now. So these kind of question can be asked in your examination. Now I'll go a bit fastly from here because I need to cover rest 3 groups, group 16, 17 and 18. The thermal stability of hydrides of group 15 follow which order? The thermal stability of group 15 decreases down the group. So NH3, PH3, SH3, simple as that, right? Thermal stability of hydride is what? Decreases down the group. Next is group 16, we call it oxygen family. There is one more name we use to dedicate them. We call them chalcogens. We called them nictogens, group 15. We call them chalcogens, meaning salt forming, no yaar, ore forming. You all know majority of the ores in the earth crust are found in the forms of oxides and sulfides. Majority of the ores are found in the form of oxides and sulfides. And yes, that is why we call them chalcogens, means ore forming elements. Group 15, oxygen, sulfur, selenium, tellurium, polonium and livermonium, Lv. So these are the elements which we need to discuss under group 16 element. Before starting their properties, let me get you to the bestest possible way of explaining their electronic configuration. We all know their general electronic configuration will be NS2, N-2, F14, N-1, D10 and then NP4. Always remember this is something that will be used as a general electronic configuration. Oxygen and sulfur are metal, selenium, tellurium are metalloids and livermonium and polonium are metals, and both of them are radioactive. So in order to discuss their electronic configuration, let us move to the next page. oxygen, sulfur, selenium, tellurium, polonium, livermonium. Can you help me to identify their atomic numbers? We all know their gaps of the atomic number, that is what we call them. What do we call them? I forgot, yaar. Magic numbers. 8, 18, 18, 32, 32. Coming to first element with atomic number 8. 8 plus 8 is 16. 16 plus 18 will be 34. 34 plus 18 will become 52. 52 plus 80, this 32 will become 84, and 84 plus 32 will become 116. That is livermonium. Now is the time that we should get their electronic configurations done. How to write their configurations, everyone? Oxygen is very simple. With the end of first period, we start second period element oxygen. Helium is having atomic number 2, helium. Then we have 2s2 and simply 2p4. See, check it out. Check out this general electronic configuration. Check out this general electronic configuration. ns2. Why is it not visible? Okay, anyways, I won't write up to there. I think this is visible now, or if not, yes, Rahul, yes, you're right. Finally, now we have come to group 16 we were discussing. I got some trouble in meanwhile. So what I'm explaining you, using this general configuration, we can apply this over here, and sulfur will become what? End of the second period neon, 3s2 and then 3p4. Then selenium will become argon, 4s2, 4 minus 2f doesn't exist, 4 minus 1d does, so we'll write it 3d10 and 4p4. Then tellurium, we have helium, neon, argon, krypton, xenon, radon, oganesson, 5s2, then 5 minus 2f doesn't exist, 4d10 and 5p4, 6s2, 4f14, 5d10, and then we have 6p4. Similarly, seventh period element is there, livermonium, 7s2, 7 minus 2 is 5f14, then we have 6d10 and 7p4. So guys, this is how I usually write the electronic configuration. I want you people to stay comfortable while writing the electronic configurations, and do remember that there is only one part where we can see that the configuration may face some So this 3D has poor shielding. Then we have 4D which has 4D which also has poor shielding. Then D and F, both of them have poor shielding, and then another D and F will be having the poor shielding, like that. We call this, let me see if I can have this arrow. Four F14 are lanthanides. 5F14 are actinides. So lanthanide apply lanthanide contraction, actinide will apply actinide contraction, and due to which Z effective will increase, size will decrease, and inert pair effect will start operating. This NS orbital starting from here, this one, this one, this one, and this one, these all will become what? Inert. Becomes inert. This becomes inert due to poor shielding of D and F subshell, and that is why we call it inert pair effect. Now let us move forward with their occurrence. Where does oxygen exist? Mostly oxygen is found in the atmospheric gases, 21% by volume. So the most abundantly it is found on the most abundant element on the earth. This is most abundant element, which is 46% by mass. Air also contains around 21% by volume. The abundance of sulfur is actually in earth crust is very low, that is around 0.03 to 1%, and it exists primarily in the forms of sulfates and sulfides like gypsum, calcium sulfate, dihydrate. Epsom salt is magnesium salt. Birite is BaSO4, galena is lead sulfide. So mainly it exists in the form of some ores of sulfides. This is chalcopyrite, copper sulfide, copper iron sulfide. It is also found in the form of H2S in volcanoes. This H2S, which is hydrogen sulfide, is a very smelly, rotten egg smelling gas, and this is how volcanoes smell like. Organic matter such as eggs, proteins, garlic, onion, mustard, hair, wool containing sulfur. Selenium and tellurium are found in metal such as metal selenide and telluride in the sulfide ore as an impurity. Polonium is radioactive and it is formed by the decay of thorium and uranium minerals. Livermonium is a very short-lived species which is synthetically synthesized in the laboratory, and this has an electronic configuration of this. We all know about it, and that's how we are defining it. Here we end with their occurrence. We all know where does oxygen, sulfur, selenium, tellurium, polonium and these elements exist. Apart from their existence, now we'll come to the another property called as their periodic properties. One of them is atomic and ionic size. There is nothing as such which is in opposite to their mentioned property. So their simple atomic size you can find. Oxygen is smaller than sulfur, is smaller than selenium, tellurium, polonium. This is the order of size. Now this size can be defined in the terms of atomic or ionic radii very easily. This is their atomic or ionic radii. It increases from top to the bottom. Very simple. Ionization enthalpy will decrease. If we talk about their ionization enthalpy, oxygen will be having the highest one. Oxygen, sulfur, selenium, tellurium and polonium. What is this? This is the order of first ionization enthalpy. This is the order of first ionization enthalpy. Very simply we can write, there is no as such exception. Or moving down the group, Z effective decreases and shielding increases easily because of the addition of newer what I can call newer shell. This is how it works. Then we have electron gain enthalpy. Everyone, this is something I wanted to explain, and I will explain this part, which is very highly important. This order follows sulfur, selenium, tellurium, polonium, and then comes oxygen. There comes oxygen. This is the order of electron affinity 1. But why? What is so wrong with oxygen? Why did oxygen go at the lowest magnitude of electron affinity, or lowest electron gain enthalpy, magnitude wise we are talking about? So for this I will explain you this part, that where does it apply. Even group, every group it works. Group 13, 14, 15, 16, 17. We don't talk about electron affinities of the noble gases, but yes, up to them. What do we see? That we all know their first element belongs to the second period, which is boron, carbon, nitrogen, oxygen, fluorine, and there comes the third period. So third period we have aluminium, silicon, phosphorus, sulfur, and even chlorine. Okay, you will find that generally what do we see? That electron affinity 1 decreases down the group. But for above mentioned groups, electron affinity 1 for the member of third period will be higher than the electron affinity 1 for the member of second period, due to extremely smaller size of second period element that repels the extra electron to accept. Are you guys getting what I'm trying to explain here? I have already raised this issue. I have already submitted my feedback from my end, and we should start having some English classes also. Now it is up to the management, and they will take a call, and whatever the update comes, I will definitely let you know. Okay, don't worry everyone. I'll do. We'll try our level best. Now this part is absolutely clear to all of us. So guys, I must give you this thing as an homework to all of you, because this is what it has been asked previously for so many years. Homework is, you need to write the first electronegativity EA1, or we call it the magnitude of delta H, electron gain enthalpy 1, not order, for group 15, 16, 17. You need to identify the order of group 15, 16 and 17, because this is what we are studying now. So always remember this order. Anyways, EA1 for group 15 somehow varies like P phosphorus, nitrogen, phosphorus, arsenic, antimony, bismuth, and then comes nitrogen. In the similar way, EA1, if I talk about the group 16th, sulfur has maximum sulfur, selenium, tellurium, polonium, and then comes the oxygen. But in case of EA1 talking about halogens, fluorine will become at second part, fluorine, then comes chlorine, fluorine, bromine, iodine, astatine, tennessine. Always remember this. I have already given you the answer of your homework, so do revise them, have analysis on their data of EA1, and then get the confirmation on the values which I am writing. So that is how we have been decided the electron gain enthalpy. Now we are coming to the another very important term that we use as their periodic property is called as electronegativity, and it's very obvious that electronegativity keeps on decreasing moving down the group, because going down the group elements become wider or broader in the size, vast in the size. Nucleus is not that much closer to accept the shared pair of electron, right? So that is why electronegativity decreases. Oxygen, sulfur, selenium, tellurium, polonium, this is the order of electronegativity. The metallic character increases from oxygen to polonium moving down the group. Oxygen has second largest electronegativity. I know its value on Pauling scale right after fluorine. So this has 3.5. Sulfur has 2.4. Selenium is around 1.8. 1.7. I don't remember exactly, but nearby to that. 1.8, 1.7, 1.6, like that. Then we have physical properties. Physical properties as in their appearance, their physical state, melting boiling points, and the densities. Talking about oxygen and sulfur, they are non-metals. Selenium and telluride are the metalloids. Polonium is a metal which is a radioactive element and it has a half-life of 30.8 days. That is something that we do not need to remember. All the group 16 elements show allotropy. We all know, like allotropy in the case of O3, sulfur is acid, selenium, tellurium, etc. They all show allotropy, and that is how their molecules are written. Their molecules exist as. Oxygen doesn't form single bonds usually with oxygen atom as a peroxide. So oxygen can give you O3, not O8. All group they exhibit, and density, melting point, everything increases down the group. Why is it so? Because of the size. Size increases and their melting boiling point and everything will increase. There is an exception for one thing, that melting and boiling point are higher for tellurium than polonium. Okay, I am already, like, I have made this a star mark because this is an important part of this particular trend, that if we are understanding melting and boiling point, tellurium must have greater melting and boiling point than polonium. Also, there is a large difference between the melting and boiling point of oxygen and sulfur. And why is it so? Because oxygen is very smaller in size, O2, and it exists as gas. Sulfur exists as a solid, and its S8 exists as a polyatomic molecule. Right, everyone? O2 is gas. Rest others are solids. Only oxygen is gas. Only oxygen is gas, everyone. Rest other are the solids. हाँ सर, आवाज़ नहीं आ रही, क्या करें? अब आ रही है. सर मैं तो हूँ नहीं यहाँ पर उस समय. 15 से 20 मैं तो घर जा रहा हूँ, तो इस वजह से. आप बताइए. तो यार कर तो लेता मैं तो मैनेज, लेकिन वही है ना कि मैं हूँ ही नहीं यार यहाँ पे. इसी अक्टूबर की बात कर रहे हो ना? नहीं हो पाएगा. कोई नहीं, मैं किसी से पूछ लूँगा अगर मेरे नॉन में रहेगा तो कोई. अच्छा अच्छा, अरे सर मन तो मेरा था, लेकिन वही है ना कि अब सर एक्चुअली में वही है कि जो अभी मेरे को बहुत सारी चीज़ें फाइनलाइज करनी है, एक टाइम पे इतनी छुट्टियां मिल Hello, hello, hello. Okay, my bad everyone, my bad. Am I now audible? I turned it off meanwhile when I left the room and went somewhere. Anyways, this is my bad, and I think now it is absolutely audible. So meanwhile, I already have explained you physical properties are already covered. This question was the only question that I skipped it because of the voice was on mute. Same property, same period we talk about ionization enthalpy of which element will be higher, group 15 or 16. We know group 15 will have higher because they have stable inert gas, they have stable half filled piece of shell configuration. Group 16 do not have so. That is what I explained here, that group 15 will be have a larger ionization enthalpy than 16. I also gave you an example of second period element, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, using the electronic configuration whichever comes under the stable configuration, like 2s2 fully filled configuration, 2p3 half filled configuration, 2p6 fully filled configuration. We have to shift them by one number as in, we all know that moving left to right Z effective increases, ionization enthalpy must increase, but boron will have lesser than beryllium, oxygen will have lesser than nitrogen, neon will have highest of all of them. That is what I did. Group 15 is already explained, dude. Just visit the lecture from initial and you will find complete group 15. Okay, now let me take you to group 16, and because try to understand, buddy, we have 15, 16, 17 and 18, and I started this chapter by 4 o'clock. Now my target is to complete all the groups in a day. So that is why please allow me to move forward from here. And this is how oxygen versus S8 molecule look alike. Why can't oxygen form O8 molecule? Because oxygen can form p pi back bonding, due to which it exists beautifully in the form of O2. But S cannot form the p pi bond. That is why it makes single bonds with 8 number of sulfur atoms and forming S8. Why is there a large difference between the melting and boiling point of oxygen and sulfur? Because oxygen is extremely smaller than sulfur. What I am talking about, oxygen, O2 and S8 in their molecular form. Another question, why oxygen is a gas, why all are solid? Because oxygen exists as O2. There is a smaller molecule, and thus smaller molecule has a lesser van der Waal force of attraction between the molecules. Talking about S8 or others, they have large sized molecules. There is a higher van der Waal forces of attraction. Let's come to the question part. Let us try solving some of the questions. There starts, sir, how was the PIQ asked? PIQs are asked in the same type only. And let me remind you this part, that from 2024 only, JEE Main 2024 and onwards, the syllabus is revised, and that is why the previous PYQs were not so much relevant, because they were kind of like they belong to the properties of the important compounds of these elements, group 15, 16, 17, like that, or some other things which is right now have been eliminated from JEE point of view. So for JEE Main, whoever are preparing, only need to focus upon their periodic properties, their physical and chemical properties, and their trends and their compounds. What compounds can they form with halogens, oxygen, water, their reactivities and all. This is how the PYQ will be asked. I'll give you some of the examples which have been asked as PYQ in the previous years, but this is how the question will be asked in your JEE Main 2025 exam. The question says that which of the following has the extent of highest electron affinity? As I told you guys, sulfur has the highest one. Second period element have the higher than the first period, third period element have the highest, higher electron affinity than the second one. And in group 16, I already have shown you that in group 16 order, what is the order of electron affinity first? Oxygen has the lowest one, then sulfur becomes the highest one. Sulfur, selenium, tellurium, polonium, and then we come to the oxygen, which has the lowest electron affinity, first electron affinity, or the magnitude of the electron gain enthalpy. Next, the catenation property is maximum in group 16,4. Catenation property is maximum for what? I guess sulfur is the correct answer, as sulfur can form acid very easily, right? Now let me give you the overall order. The most versatile element that forms the catenation is carbon, then followed by sulfur, silicon, oxygen, nitrogen, etc. Like this works. So sulfur will be the correct answer here. Next question. Now we have come to the chemical properties of group 16 element. Group 16 elements have their chemical properties by reacting with different kind of elements. Number one, let us talk about their oxidation state. What oxidation state usually they pursue, they possess is -2. Oxide, sulfide, arsenide, bismuthide, not arsenide, bismuthide, selenide, telluride, like that. -2 oxidation state. And decreasing down the group, we can see that positive oxidation state will go on. But common oxidation states are these: -2 for oxygen, -2 + 2 + 4 + 6. No need to remember this. We already know the configuration. We already know how many electron does exist in their valence shell. We can easily assign the oxidation state as per the molecule. But always remember that there are two oxidation states that keeps on decreasing while we moving down the group. -2, because oxygen being typical non-metal can show you -2 oxidation state. Sulfur can show you -2 oxidation state, H2S, H2O. But going down the group, we have metals introduced over there. Metals have higher like positive oxidation state, and that is why -2 won't exist with them. So -2 decreases down the group as the electronegativity decreases, and +4 oxidation state increases down the group, increases their stability because of inert pair effect, and +6 also decreases due to same inert pair effect. Due to inert pair effect, because while moving down the group, insertion of D and F subshell take place, which have poor shielding, due to which Z effective increases. NS electron comes very close to the to the nucleus. NS2 electron become inert to participate, and whatever it is left in the P subshell, that is P4. So P4 can only participate in bonding rather than NS2. And I have already explained this part to you. I don't need to explain this much too many times. Oxygen can show you +2 oxidation state in the case of OF2. And it also shows +1 in the case of O2F2. But oxygen has varieties of oxidation state with it. Sulfur, selenium, tellurium usually show +4 oxidation state in their compound with oxygen, and +6 with their compound in sulfur, SF6, SCF6, like that. Then we have the bonding in +4 and +6 oxidation state are predominantly covalent in nature, because covalent, I told you, as per the Fajan's rule, the covalent nature is directly proportional to the polarization. The polarization is directly proportional to the polarizing power of cation. So higher is the positive charge on cation, higher is the polarizing power of cation, higher is the polarization or the covalent character. That is how we explain this part. Now we have chemical properties of, we are not having chemical properties, okay, we have it, but take the account of oxygen, which has exceptionally different properties because of its smaller size, high electronegativity, anomalous behavior of the first element. That is what in our syllabus of JEE Main. So H2O has the hydrogen bonding, H2S does not. That is why H2O exists as liquid and with higher or stronger intermolecular force of attraction, but H2S exists as a gas. The absence of vacant orbitals in oxygen cannot lead oxygen to make more than 4 bonds at once. Oxygen cannot make more than 4 bonds because it belongs to second period element. All second period element can form 4 bonds only. 4. That's it. Reaction with hydrogen we have a reaction with hydrogen, and talking about their hydride, they usually form H2E type compound like H2O, H2S, H2SC, H2T, H2P, polonium, like that. Their acidic character increases down the group. As we have already discussed, their basic character decreases down the group, their acidic character increases down the group. Easily hydrogen can depart from there. That is why hydrogen will be easily available due to decrease in the bond enthalpy of dissociation of this. Thermal stability decreases, just like in the case of 15th group element. There we have, due to the decrease in the bond enthalpy for dissociation of hydrogen and metal bond. Reducing property, we talk about reducing property increases from H2S to H2T because of the availability of oxygen. Availability of oxygen. But H2O does not show you reducing property because of stronger hydrogen-oxygen bond. Melting boiling point is very easy, decreases down the group, but increases down the group, but H2O has highest because of the, so that is what it has been explained there. I don't need to explain this too much because we already have discussed about it, that H2O, H2S, AC, T, PO we talk about. This has exceptionally higher, this has highest melting point and boiling point. The reason is very clear, due to H bonding. But from here to here, boiling point and melting point increases due to increase in size. Size increases, intermolecular force of attraction called as van der Waals force of attraction increases. So that is how it follows the order which is mentioned here in front of you. So now number 2 is the reaction with oxygen. Okay, reaction with their oxygen. So how do they react with oxygen? They generally form two type of compound. One of them is EO2 and EO3. EO2 and EO3. So with oxidation state of positive 6 and positive 4, just like SO2 and SO3, sulfur dioxide, sulfur trioxide. Ozone and sulfur dioxide are the gases, while SCO2 is a solid. Reducing property of dioxide decreases from SO2 to TiO2 because why does it decreases down the group? Because tellurium dioxide is more stable, doesn't want to get reduced easily, and sulfur can easily undergo from positive 4 to positive 6 oxidation state. Since it is oxidizing itself, then it will reduce the front atom or ion, right? Because of positive 4 oxidation state stabilizes down the group. SO2 is reducing agent while TiO2 is an oxidizing agent. Very nice. Okay. Then sulfur, selenium, tellurium also form EO3 type of oxides, and both the oxides are acidic in nature. Moving forward, reaction with halogen. So now elements of the halide EX6, EX4, EX2, this kind of halides have been formed by, like you can have this example, SF6, SCl4, SCl2, etc. These type of halides have been shown. The stability of the halide is in the order of fluoride will have highest extent of overlapping with the element, and then chloride, bromide, iodide. Higher is the size of the cider atom, lesser is the accommodation around this particular atom, higher will be the we can say steric factor. See, only SF6 exists, only except SF6 exists, others do not exist in EX type compounds. Only hexafluorides are stable, and they are gaseous in nature, and they also have octahedral shapes. Their shapes somehow look like this: sulfur, with 6 halogens. We can see that these 4 are in the plane. This is above the plane and this is beyond the plane, like that. Above and below the plane only. Or there could be another way. No, it's fine then. This is also fine. EX4, if we talk about SF4 is a gas, SCF4 is liquid, TF4 is a solid. Do remember this part because we all know only this is the part of our JEE Main 2025 syllabus, their physical, chemical and such kind of properties. So I would request you, do remember these part, make short notes out of these completely, right? Sir, what is the property of PO? Even I don't know what is PO. Polonium, we are talking about. Polonium doesn't make too much of compound, and being radioactive in nature, we do not study these compounds very well. Compounds that exist in the form of like as a radioactive, we don't study them very well because we are unaware about their properties. Sometimes they have smaller decay life, they have smaller half-lives, they can decay easily. That is why we do not study their properties, but we will take into account those elements which exist naturally, normally. Now coming to, we have their structures. sp3d hybridization will be there in SF4 and trigonal bipyramidal will be their geometry, and because of their one lone pair they may have different shape is seesaw. I can explain this part. Take this example. They are asking about sulfur tetraoxide. Sulfur has 6 electrons inside it. 6 electrons are there, 4 bond pair it is forming, and 1 lone pair will be there. That is why total of steric number 5. If total is steric number 5, then hybridization will become sp3, 1s, 3p and 1d. Geometry will be no doubt trigonal bipyramidal, and shape is what which is dependent upon its first you need to draw the geometry and then you need to identify. So this is sulfur, and we know that single bonded elements will come top and down on the axial positions. In the equatorial position we need to put 1 lone pair and 2 sulfur atoms. How does it look like? Seesaw. Hiding this lone pair, the rest of the shape will be visible. Shape is seesaw. Check it out. So keep on liking the session, everyone. Those who haven't liked the session, do like the session on priority. So now reaction with halogens we talk about. There are two type of there are various type of compound, SF6, Cl2 and this all. So out of these, now we talk about the EX2 type compound. So all the elements except oxygen, they form dichloride and dibromides. Oxygen doesn't form OCl2 and OBr2 because oxygen is very small in size, cannot accommodate large size halogen atoms like chlorine and bromine with it, forming the molecules with them. But yes, oxygen can form hydrides, H2O is there, and oxygen can form other compounds with rest of the members, forming SO2, SO3, like that kind of compound can form. So monohalides are dimeric in nature. They exist in S2F2, S2Cl2, S2Br2, Ac2Br2, like that. And they undergo disproportionation reaction as given below. So whenever you heat these compounds, they dissociate, giving you selenium and selenium tetrachloride. One of the important reaction. Why is H2O a liquid and H2S is a gas? It's very simple, because H2O has the hydrogen bonding, H2S does not. That's why higher attractional energy between two molecules can hold them, forming a liquid, but H2S doesn't have that much interaction and it roams around like a gas. The acidity of diprotic acid in aqueous solution increases in the order, increases down the group. Water is neutral, H2S is acidic, H2SC is more acidic, H2T is even more. This is the order of acidic strength, Ka. Always remember this thing. H2STE, A is the correct answer. A is the perfect answer. Why does not oxygen H2O possess the reducing property? Because of oxygen hydrogen stronger bond. Stronger bond. H2O is very stable molecule. Doesn't give hydrogen to reduce. Why sulfur dioxide is reducing and tellurium dioxide is oxidizing in nature? Sulfur oxide can go to SO3 plus 6 plus 4 by losing 2 electron. Stable. So what is it doing, by the way? In this process, what is happening? Oxidation, and the one which undergoes oxidation is called as reducing agent. But tellurium oxide positive 4 cannot undergo this reaction, so doesn't work as a oxidizing agent, but upon heating it may give you tellurium or tellurium monoxide kind of product. So let us say this is undergoing reduction and this is undergoing oxidation. Oxidation doesn't occur, reduction occurs. That is why that's why it will work as a oxidizing agent. Something that reduces itself will be working as an oxidizing agent. Always remember this key points. Sir, only sulfur, selenium dimeric in nature and their elements can form dimeric. No, nobody. Only these exist. That is why I told you this part. It's very important part. Do remember this part. Only these exist. Examples are S2F2, S2Cl2, S2Br2, SC2Cl2 and SC2Br2. These are the only one which exists in the dimeric form. These are the monohalide. Monohalide means ratio of halogen to the element will be 1. S2Cl2, S2Cl2, 1 sulfur, 1 chlorine per molecule, like that. Sir, no sound to the video. Let me check. No, it's properly audible. Sound to the video. It's properly audible now. Tung, dung, 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 tung, dung, dung. Array, I have wasted this question. Anyways, somebody was asking me about PYQs. So see, it's a previous year question asked back in JEE Main 2020, this question. Okay, the question says that if the boiling point of water is 373, the boiling point of H2S will be definitely lesser than that, less than this, greater than 300, maybe less than that. What is this 300? I don't know. Less than 300. Okay, take this as remember this part only, because H2S doesn't have any H bonding. It doesn't have any H bonding, no H bonding, thus low boiling point. Which of the following is the correct reducing nature of UO2? Reducing nature means you all understand. Who can reduce, which can be oxidized to itself. Tellurium cannot oxidize itself. Sulfur, then this will be the correct answer. Sulfur dioxide, selenium dioxide, tellurium dioxide. Probably. Let us check it out. Absolutely correct. Next question. The order of stability of the halide of the sulfur. Everywhere you go, it will follow the order of fluoride, chloride, bromide, iodide. This is the order of reactivity. If this is the order of reactivity, once they react, they will make more stable products. So correct answer should be B. Next question is there, although this question is not a part of your syllabus as of now, because this is what we are studying is the oxo-acid of sulfur, but oxo-acid we don't study in. JEE has removed this part, but anyways I'll give you the idea. H2S2O7 is called as oleum. This structure is S double bond O OH double bond O OH. Then we have H2S2O8. We call it we also call it like pyrosulfuric acid or disulfuric acid. No, pyrosulfuric acid is this. This is called as peroxide disulfuric acid, and we call it as Marshall's acid. And the structure is somehow like this. All the oxy-acids have this thing in common, double bond O and OH group, but there is a peroxide bond. This peroxide bond leads to change in the oxidation state of sulfur also, but this is how it look like. Now the question is been asked to us. The question is number of S double bond O bond and SOH bond present in both. I think this is same in the number. S double bond or how many? 4. So and SOH are also the same only. So the correct answer should be 4 and 2, 4 and 2, I guess. 4 and 2 and 4 and 2 as per me. I think D should be the correct answer. I think D should be the correct answer. Next question is the similar question, and we got to tell them the increasing number of pi bonds. So let us say H2SO3, H2SO4, H2S2O7. I guess H2S2O7 will work or will win. Number of pi bonds will be higher. It has been asked in JEE Main 2027 because this is an older question. Nowadays this is not in the part of your syllabus, the structures of these oxo-acids and all. Still take the idea. Sulfur, H2SO3, how does it look like? It gives you one lone pair, one double bond O, one OH like this and another OH like this. Similarly, this will give you sulfur, double bond O, OH and another OH. This is something which I recently told you. S double bond O is there, 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 OH and OH. Now what has been asked? The number of pi bonds. So how many pi bonds can you see here? I think there is one pi, there are like two pi's, and there are 1, 2, 3, 4. So correct answer should be H2S2O7, H2SO4 and H2SO3, the decreasing order. So that was your JEE Main 2017 question, and now is JEE Main 2019 question. 19 question is here. The oxo-acid with sulfur that doesn't contain any bond between sulfur atom, where you cannot find any bond between sulfur atoms. So H2S2, H2S4O6. What is H2S4O6? I don't know about this H2S4O6. What is it? So H2S2O3. Dithionic acid. Oleum. H2S2O4. S2S2O4. What is it? S2S2O4. Okay, there could be a possibility. Okay, 8 minus 2 is 2 plus 2x minus 8. X is 6. I think there will be an oxy bond. There is an oxy bond like this. Check it out now. 1, 2, 3, 4, 5 S2S2O4 we have to make. The oxo-acid of the sulfur that does not have between sulfur bond, which does not have, I think now only one option is left to answer. 3 option is there. Okay, the correct answer was S2S4O6. Oxo-acid between, I think this is incorrect, incorrectly mentioned there. Okay, let me just take this question. What is it, by the way? I think we are right. This question is wrongly answered in this quiz, but anyways we received the correct answer. C is the correct answer and not this one. The only correct answer will be C. So now we have group 17 and we have group 17 and we also have group 18 and we will be starting group 16 and 17 very soon. But before that we will take a bit smaller break of 15 minutes so that I can come and we can start this very soon. So let us have a 15-minute break from here. So those who haven't liked the session, do like the session, everyone. And do not go anywhere. I'll be back. Stay tuned. So guys, I'm back. Hopefully you all have enjoyed. A 30-minute break. Yeah, हाँ, thank you. Well, okay. Let it be a 30-minute break. Okay, no problem. So anyways, now we'll finish the remaining part of this chapter, and which is group 17 and group 18. So from here I would hardly take a half an hour, and we'll finish this complete session. There we go. Hello. I think I'm audible, no? Yes. So guys, now we have come to group 17 element. Group 17 elements, actually we call them halogens. What do we call them? Halogens. What is the meaning of halogens? Halogens means salt forming. So most of the ionic compounds they have anions in the form of halide ion. Just say most probably like sodium chloride, sodium bromide, potassium bromide, potassium chloride. So these type of elements are called as halogens, that means salt forming. Next we have introduction about them. So let me take you to their common or general electronic configuration. So first of all, we have the general electronic configuration. This is NS2, N-2F14, N-1D10, NP5. So basically consecutively I'm adding one extra electron. I started it from 13th of the group. There was NP1, then I went to 14th, NP2, NP3, NP4, like that. NP5 is your 17th group element we are talking about. Their general electronic configuration is this. Now let us talk about what elements are there and how to write their electronic configuration. So the elements are fluorine, chlorine, bromine, iodine, astatine, and TS stands for tennessine. So these are the electrons, these are the elements which belong to 17th group. Now coming to their atomic number, we all know their deltas of the atomic number. We call them magic number is very common, 8, 18, 18, 32, 32. So using this data you can write down their atomic number. Fluorine has an atomic number of 9, 9 plus 8, 17, 17 plus 18 will be 35, 35 plus 18 will be 53 I guess, 53 plus 32 will be 87 I guess, sorry 85, and 85 plus 32 will be 117. This is the atomic number. Now writing down their electronic configuration, very simple to write. Just put helium in the second period element. Why? Because the first period ends with helium, next comes the second period. Second period has the maximum value of principal quantum number as second 2. So use this formula 2s2. Do we have any 2 minus 2f? No, 0f is not possible. 2 minus 1d is also not possible. Simply write 2s2 2p5. Now going for chlorine, we have neon 3s2 3p5. Coming to bromine, we have argon 4s2. Now 4 minus 2f might not be possible, but 4 minus 1d is there. So we will write simply 3d10 and then write 4p5. Now going for iodine, we have krypton 5s2. 5 minus 2f doesn't exist, but 5 minus 1d does. So we'll write it down 4d10 and there comes 5p5. Then astatine, right after krypton it becomes xenon. Then 6s2, 6 minus 2, 4f14. Then we have 5d10 and 6p5. So always try to write the electronic configuration just like I do, because that is the most easy method I find to write it down. Tennessine, we can go for C. Helium, neon, argon, krypton, xenon, radon. Put Rn here. 7s2, 7 minus 2, yes, 5f14 exists. Then 6d10 exists. Then 7p5. 7p5. That is how we write out the electronic configuration. So what is the noticeable thing in all these configurations? The noticeable things are, these are the noticeable thing, that poor shielding of 3D, poor shielding of 4D, poor shielding of 4D and 5D, and then poor shielding of 5D and 6D. These are the something that to be noticed. Rest all are the same only. And you might have observed then even in 15th group and 16th group, we have done the same exercise. We try to do the same thing and we know how to write down the electronic configuration, and this is how it completely works. The very first thing that we need to study is their occurrence. So where do you find the fluorine? I told you once, apatite family of phosphorus there we used to found. Apatite family, Ca3PO4 whole thrice dot CaX2, where X was the halogen. You can take down chlorine and phosphorus over there. So in the fluoroapatite family, you can find out fluorine. So take this thing as an example. Fluoroapatite is the example of where can you find the fluorine as a salt. Cryolite is one example, fluorospar is one example, and fluoroapatite. These are the some very well known salts we know. These exist in the earth crust as an insoluble fluoride, you can find them. Then we have the small quantities of fluorine is present in the river water plants and in bones and the teeth of animals. So basically you can find it over there. And the teeth of the animal is also made up of the same chemical composition called as the what do we call it? Fluoroapatite only. That is calcium phosphate dot calcium fluoride, like that. Chlorine, where can you find the chlorine? Chlorine, the biggest resource of chlorine is the dissolved NaCl in seawater, right? So seawater contains too many chlorine salts, especially chlorides, bromides, iodides. These salts are dissolved in water only, and you must know that hard water is something that contains calcium and magnesium ions in it, but in what anionic form? Calcium exists as CaCl2, SO4, sorry, not SO4, but CaHSO4 whole twice bisulfate, and not like that, maybe bicarbonate they exist, but so the seawater also contains some of the salts like sodium chloride and carnallite, which is a salt of, it's a double salt of potassium chloride and magnesium chloride dot 6H2O. So this is what the dried seas contains of these compounds. Dried seas means if you evaporate, collect the salt present in water, then seawater, you will find sodium chloride and this carnallite as a major constituent. Where do you find the iodine? So iodine is mainly found in marine life contains iodine in their systems. Various seaweeds are there. Seaweeds as in some of the plants found in sea, they contains 0.5% of iodine, and there is Chile saltpetre that we right now discuss only contains up to 0.2 form of sodium iodate. So basically the composition will be Chile saltpetre is NaNO3 dot NaIO3. So sodium iodate and sodium nitrate, they two exist together. Do remember this part. So that is all about the existence. Rest all other exist in the traces as an impurity on the given halide sources only. So main three have been already discussed, that is fluorine, chlorine and iodine. Now comes tennessine. Where can you find tennessine? Tennessine is a synthetic radioactive material that is the element which is man-made element, and it's radioactive in nature, and only a very small amount of this compound can be prepared, or this element can be prepared. Its half-life is millisecond, and that is why the chemistry of this cannot be established. And you might have observed, like I've been teaching you from past few time, and we have noticed that we do not consider the periodic, chemical and physical properties of these compounds which are radioactive in nature. The major reason behind it is their half-life. Their half-life is very small, that they can undergo radioactive decay by the time of their chemical reaction, and that is the only reason for which we do not study their chemical and physical and other properties together, and we study the thing for the rest of the element which are not radioactive in nature. We have another simpler and similar kind of properties. Very first of them is ionic and atomic radii. We all know, moving down the group, atomic or ionic radii increases. So we will see that fluorine will be smaller than chlorine, will be smaller than bromine, will be smaller than iodine, will be smaller than astatine. This is the order of size. Now you can consider this thing in the terms of an ionic size, like with 1 minus charge, or you can consider it with the covalent radii with an atomic size. Whatever you want to take, you may take into the account. Halogens have smallest atomic radii in the period. Why is it so? Because of their maximum Z effective. When we move left to the right in a period, their Z effective increases, their sigma or the repulsion, electronic repulsion increases also, but overall Z effective increases. That is why their size keeps on decreasing. So atomic and ionic radii from fluorine to iodine increases very easily with the increase of their principal quantum number, or the number of shell, like n we are talking about. Fluorine is the most extremely small element. So guys, ionization enthalpy delta Hi 1 naught, which is also termed as IE1. If we talk about their magnitude, so this will be fluorine has the highest, chlorine, bromine, iodine very easily. And electron gain enthalpy I have already told you. Chlorine has the most electron gain enthalpy, then comes fluorine, bromine, iodine. This is electron affinity 1, or the magnitude of delta H, electron gain 1, like this. A tendency to accept an extra electron is called as the electron gain enthalpy, and this is maximum for chlorine. And not just maximum among this group, chlorine has maximum electron affinity among all modern periodic table. All the elements of modern periodic table, chlorine has the highest first electron gain enthalpy, or the tendency to accept the electron, an extra electron toward itself. Fluorine, being very small in size, sometimes repels the incoming electron, and that is the only reason for which fluorine doesn't have the maximum EA1, and it is chlorine which has the highest EA1. So down the group we go. We already know about it. Now let us move forward. Electronegativity is very easy to define, guys. It decreases going down the group because size increases. Size increases and electron becomes far from the nucleus to accept them, to attract them. So now checking their electronegativity, and on the Pauling scale, fluorine has the highest electronegativity of 4, 3, I don't know how come 3, around 2.9, around 2.8 or 2.7. This has a 2.2. So this is how their electronegativity work. I'm not sure about these readings. So this is a taking, this has been taken as an idea only, but what we can observe is the trend. The trend says that fluorine will be having the highest one, and fluorine has the highest electronegativity among the entire periodic table. So this group, 17th group, is highly important to us because this is where we study a lot of the properties which are interlinked to each other. A lot of properties are there which are like extremely high or extremely low. Like fluorine has the highest electronegativity, chlorine has highest electron affinity. So this is how we can define this particular period. Now try some questions on the basis of same the properties we studied. Periodic property, which is most electronegative? No other, which is more electronegative? Chlorine. We know their electronegativity on Pauling scale. Chlorine has 3, this has 2.7. Which of the following do you find has the greatest electron affinity? It's chlorine, and it has the highest among all elements of modern periodic table. Modern periodic table has the highest electron affinity for chlorine. The electron gain enthalpy with the negative sign is less for fluorine than chlorine. Why is it so? Because of the high ionization enthalpy. Smaller size of fluorine atom is the one responsible for the repulsion of the incoming electron. This is fluorine, and this is already having, let's say, this electron. So in an extra electron, when it comes, it repels. But talking about the chlorine, this is chlorine. 3 electrons are quite far from each other. If it accepts electron, easily accepts, forming what? Cl minus. This was the question asked back in 2013. 2013 this question was asked, guys. So we have covered this part already. Okay, I don't know why is it repeated anyways, but there are so many things which are included here. For astatine and tennessine also you can study. Astatine can only find in the earth following decay of the thorium and uranium. Okay, both of them are radioactive. We have covered this part, 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 we have covered this part. This we have covered. Now comes their physical properties. Okay, now comes their physical properties. So physical properties are very simple, like their physical state, like their physical, like their smell, touch, or boiling, melting point, density. These are the properties that we need to discuss. First of all, fluorine and chlorine are gases. Bromine is the only liquid. It is the only liquid non-metal. Guys, in our modern periodic table, there are around 93 metals and 7 metalloids. Remaining 18 are the non-metals. Out of these non-metal, mostly of them exist in the form of gases or in the form of solids. Gases as in hydrogen is a gas, fluorine is a gas, chlorine, helium, neon, argon, krypton, xenon, radon, all of them are gases. Now talking about the solid part, carbon is solid, sulfur, phosphorus, these are the solid parts. Now coming to the only non-metal with liquid state, bromine, Br2, red colored liquid. I2 is a solid which is sublimable at atmospheric pressure. That means under atmospheric pressure or under these conditions, it exists is in an equilibrium, in a physical equilibrium with I2 vapors, gaseous state, and I2 solid as a purple colored solid. Melting and boiling point increases down the group. Why is it so? Because we know F2Cl2, Br2 and I2. Guys, what is this order all about? This is the order of size, as I told you, and all of them exist as diatomic molecule. So since the size is increasing in this order, what we can conclude over here, sir, van der Waals force of attraction, the van der Waals forces of attraction is directly proportional to the size. Higher is the size, higher is the van der Waals force of attraction. Now simply boiling point is also directly proportional to the forces of attraction. So you can derive it easily that higher is the size, higher is the melting and boiling point. Melting point and boiling point increase down the group with the increase in their size, and so that the strength of the van der Waals force of attraction acting between them. Fluorine and chlorine can easily react with water. and they usually form their hypohalous compounds with them. We'll come to that. Bromine and I2 are sparingly soluble, doesn't react very easily, but they are soluble in various other non-polar solvents such as chloroform, carbon disulfide, benzene, C6H12, cyclohexane, etc. So mostly all the halogens are colored. Why? Because of the absorption of light on promoting an electron from ground state to the higher one. Guys, if you know about halogens, halogens usually have unpaired electrons. Not like that, yeah. This is not about the unpaired electron. Anyways, we'll come to that. First of all, let us go through what color do they show. Fluorine is yellow in color. This is something that we have to learn. I'll star mark this line. Fluorine is yellow, chlorine is greenish yellow, bromine is red, and iodine is violet color. Okay. On descending, the group energy level becomes closer. Let me read it. I got to check it. Let me check it here. Okay. Anyways, so I'll give you this example. This thing is actually explained using the molecular orbital theory, that in the formation of their molecules, their highest occupied molecular orbital and their lowest unoccupied molecular orbitals are very closer to nearby, due to which absorption of light takes place, electron goes in higher state, and due to which the color comes, and that is only the reason behind the color of these compound. F2Cl2 Br2 I2 and At2, this is how they look alike. Just learn this thing, okay? The color must be known to us. This is very much useful in the analytical chemistry. Sometimes this comes in the form of like a greenish yellow colored gas released, then we must take an idea of which one was the greenish yellow. Chlorine, like that. We are talking about the bond energy. The bond energy order is not as expected. We can see it is somewhat different, and the actual bond order is Cl2 Br2 F2 and then I2. This is the actual bond dissociation energy, bond dissociation energy order. Why is it so? The reason can be easily explained. Simply 2p orbitals are having highest extent of overlapping. Fluorine must have highest bond order, highest bond energy. But why is chlorine having the highest one? Because fluorine being highly smaller in size, and 3 lone pairs on each fluorine atom is there which are repelling each other, and that what makes the fluorine bond weaker relatively than chlorine and bromine. This is what the order is followed. Do learn it, remember it. The bond dissociation energy in fluorine is abnormally very low, and as I have explained the part that why is it so, because of their smaller size, higher number of electron pair cause more repulsions. These lone pair cause more repulsion, making even this bond even weaker. Talking about their oxidation states, fluorine always it has -1, because fluorine being the most electronegative element in the entire modern periodic table, all the elements have higher electronegativity than, lesser electronegativity than fluorine. So fluorine is the one which is connected whenever to any heteroatom. It will definitely be having -1 oxidation state, and the rest of the atom will be having a +1 oxidation state, which is bonded to fluorine. So chlorine can have, chlorine and these all can have variable oxidation state between -1 to +7. And I can give you this example, everyone, that where can it show you this state? Let us take an example of chlorine. So one of the example is HCl, and then we have Cl2 as one of the example. Then we have HOCl. Then we have HOCl. HClO2, and this can also be written down as HClO, HClO3, HClO4. First of very all, let me just write their name. This is called as hydrochloric acid. This is simply chlorine. This is called as perchloric acid. Allow me a sec, everyone. पता नहीं था मुझे, मैंने वो देखा था व्हाट्सएप पे, अभी पता चला। अच्छा आपने अभी पता चला था, व्हाट्सएप पे देखा, उस पे फेसबुक पे डाला ना तूने? व्हाट्सएप पे डाला था, व्हाट्सएप पे मैं देखता हूँ, फेसबुक पे दिखा, फेसबुक पे डाला होगा, क्यों नहीं डाला होगा? तू तो हर चीज डालता रहता है फेसबुक पे, कॉपी है फेसबुक पे। तूने ये अपनी फोटो डाल रखी है, अभी तो डाली थी, अभी तो डाली, वही दिखाऊंगा। अच्छा आज ही तो डाली। ठीक है सर, ठीक है, कंटिन्यू करो, मैं आपको थोड़ी देर में। Yes. This is called as simply dichlorine or chlorine. HClO is called as hypochlorous acid. HClO2 is called as chlorous acid. HClO3 is called as chloric acid, and HClO4 is called as perchloric acid. Now talking about their oxidation state, chlorine has -1 oxidation state here, it has 0 here, +1, +3, +5 and +7. Perchloric acid with highest oxidation state of chlorine regarded as the strongest acid among all of them. Clear, okay, everyone? Avi, Panchal and Sheikh, very good evening, everyone. Guys, I don't see very normally hi hellos and all, because we started this lecture by 4 o'clock and now it is a time that I should finish this entire chapter. So that is why whenever any doubt comes, I respond you. Might not be responded you on your hi and hello, so pardon me for that. Next is your some of the questions from the the same property which we studied. The question says that which halogen is liquid at room temperature? Which halogen is liquid at room temperature? The only liquid, only non-metal which is liquid at room temperature is bromine. Now trying another doubts over here, that why solubility of halogen in organic solid increases down the group? Because solubility in organic solvent, yeah, so this happens because of the size. Fluorine is being very small in size and can easily be accommodated within water molecules. Coming to iodine, okay, also water is polar in nature. Polar nature of water helps to surround the F2 . So anyways, this can be explained in the terms of covalent nature. Actually, I was checking its answer and I was actually looking for the perfect or exactly answer. So why does fluorine exhibit only -1 oxidation state while other halogens can show you even more? So guys, it's very simple that any element which is bonded to fluorine, so that is how we decide the this is most electronegative, and because of its most electronegativity, it will always give you -1 oxidation state, but this can only have a positive one, right? But coming to even there are so many compound such as IF7. If you talk about IF7, iodine has positive 7 oxidation state, fluorine will only be having minus. I think the reason is pretty much clear to all of us. Why solubility of halogen in organic solvent increases downwards? Why does it happen? There could be multiple reasons, but I can give you 1 or 2 reasons here. So similar type of packing, similar type of bonding, similar type of bonding is seen in halogens going down the group with organic solvents. Just like in organic solvents, we have similarly non-polar type of bonding or covalent bonding. The same bonding happens in the case of this. But what about the rest? Chlorine, Cl2 can accept an electron pair. Okay, this is how we write down this equation, that whenever H2 is given to us and Cl is there, so we know it has vacant orbital, and this bonding is only done because oxygen is actually 2p orbital and this is your 3p orbital, and that's why it easily comes and attack over there, forming a compound which removes Cl in the form of Cl minus. So this gives you HOCl plus HCl. This is how it is produced. So more or less we can see that chlorine and bromine and similarly these can react easily with water, forming the compound. Another example could be, let's say H2O is reacting with fluorine. So there we can say simply HF can be formed, and 2 times of HF can be formed with half of oxygen released down. So that is the only reason for which fluorine and chlorine and bromine are highly reactive, because like chlorine and bromine are moderately reactive, fluorine is highly reactive, and that's why it gets easily dissolved in the water, forming some compounds such as HF and oxygen. Next is, let's try some questions on the properties which we right now discussed about the oxidation states and some of the chemical properties we studied. Which one of the following is not the correct trend indicated against it? This is a very good question which has been asked. Such kind of question may be asked in 2025 exam. Anybody who is watching this video from any time can have this thing. Okay, they can attend this class from anywhere you want. Which one of the following is not indicated? Okay, fluorine, chlorine, bromine, this is incorrect. We all know the correct bond dissociation energy is fluorine will not come here initially. Chlorine will be having the highest, then bromine, and then comes fluorine, and then comes your iodine. This is the actual order of bond dissociation energy. So I guess this is the only correct answer. Not correct. This is the only basically correct option. Next is fluorine, chlorine, bromine, iodine. Density is fine. Moving down the group, weight increases, mass increases, and density increases. Boiling point is the same with the size. Electron gain enthalpy is the same. Bilkul, absolutely. This is what, everything is correct here. It is correct. Only A option is there, which is bond dissociation energy is mentioned incorrectly. The non-metal that does not exhibit positive oxidation state, out of these 4, what do you think, which one of them will not be having a positive oxidation state? Iodine, oxygen. The only example is fluorine, because fluorine being the most electronegative. Being most electronegative, it exists only in the -1 oxidation state. Then we have another chemical properties such as reactivity, their oxidizing nature. So number 1 is all halogens are highly reactive, and the reactivity decreases down the group. The reactivity decreases down the group because what should I say? Actually, the bond formation, or maybe the probability or the possibility of getting attacked by any reagent, is higher in the case of F2Cl2 Br2 relatively, and it decreases with the case of I2. Iodine being very broad or wide in the size does not have an ease of getting attacked by either electron pair or by any positive charge center. That is why in every case you will find the smaller halogen will be highly reactive. These are some set of reactions given to us. All the halogens are strong oxidizing agent, and they can accept electron readily. So they can reduce themselves, and they behave as easily the oxidizing agent. Fluorine is the strongest oxidizing agent in aqueous solution, while in gaseous or in gaseous phase, and oxidizing power decreases down the group because of depending upon the which can accept the electron pair faster, like that. Halogens with more SRP will be having can displace salt with lesser SRP from its salt. So anyways, this is very much easy and can be memorized as more reactive halide can replace, more reactive halogen can replace less reactive halogen from their salt. Take an example. For an example, if I have this reaction of F2 with NaCl, so this will be 2 times of sodium fluoride with Cl2 gas displaced. Cl2 gas displaced. Chalo, now let's move to the another question. We have reactivity and oxidizing nature that were discussed. Oxidizing power decreases down the group since it depends upon 3 factors. One of them is bond dissociation energy, electron gain enthalpy, and hydration energy. Okay. So what is it telling us? That whenever we are bringing one reaction, oxidizing power we are talking about. So it requires 3 things to complete. First is the dissociation, conversion of X2 into X gaseous, acquiring it a negative charge by electron gain enthalpy, or this amount of energy is released while it has been taken 1 electron, and then the another energy is hydration energy when it goes to the aqueous medium. Also in case of Br2 and I2, the enthalpy of vaporization and sublimation are also considered, and they are in liquid and solid state respectively. Not so much rememberable thing, not required to be done. Actually this is what we it's a part of thermochemistry that we cover in Hess's law. Okay, so let me give you this answer, guys. You can check everything over here. Enthalpy of dissociation, enthalpy of electron gain enthalpy, which is generally usually negative, and then enthalpy of hydration. So what makes fluorine as the strongest oxidizing agent? That was the question. What makes fluorine as the strongest oxidizing agent? Not bromine, not chlorine, not iodine. That was the question asked here, and the answer is given over here. Using this data, you can identify which one of them is undergoing highest overall, which of the following, this entire sum will be most negative for which of the halogen, that is fluorine, and that makes fluorine as the strongest oxidizing agent. Moving next, fluorine also oxidizes water, producing hydrofluoric acid and oxygen gas. I told you this reaction. Chlorine and bromine also react with water and they produce their respective hydrohalic acid and hypohalous acid. X2 gives you HX plus HOX. So whenever such kind of reaction have been given in organic chemistry, we have seen such equations where bromine water is allowed to attack over an alkene, and we used to form there, we used to consider this as an hypobromous acid, Br positive as an electrophile and OH minus as a nucleophilic part. The reaction of iodine with water is non-spontaneous. Iodine generally doesn't react with water. In fact, I minus can be oxidized by oxygen in acidic medium, and just reverse of the reaction can be observed with the fluorine. So I minus reacts with H plus and O2, forming I2 and H2O. So iodine doesn't react easily with water. This is what it is explaining. Next is the reactivity towards hydrogen. So they all react with hydrogen, forming their hydrogen halide, and which are usually gases, but yes, they in aqueous medium produce acids. They are called as they called as hydrohalic acids. Hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, like that. And their acidic strength increases in the terms of HF, HI, HCl, like this. I told you once that whenever we talk about elements present in a group, we need to consider their sizes, not their electronegativity. So talking about their sizes, whenever they release H positive and they form I minus, F minus, Cl minus, Br minus, the stability is dependent upon the charge which is dispersed over that ion. So I minus has the most dispersed charge, higher size over there, lesser charge density, and that's why it's more stable among F minus, Cl minus, Br minus and I minus. That what makes it more stable. Then thermal stability, we talk about. Thermal stability is also follows the same bond order, because HF we have 1s versus 2p overlapping, HCl we have 1s and 3p overlapping, 1s 4p, 1s and 5p overlapping, and that makes HF as the strongest bond and most stable as a compound it exists. Here are some of the properties. Now we have chemical properties continued here, and we have the properties of their the hydrohalic acids, their melting point, boiling point, bond lengths. Bond length is very much easy to explain, which we have already covered, and boiling and melting points will be increasing moving down the group, except HF, because HF contains what? This. Why is it maximum? Why is it maximum? Because of due to hydrogen bonding. Even in the solid state or in the liquid state, HF has the higher extent of hydrogen bonding and higher melting and boiling point. Similarly, bond length we compare. Bond length will be smallest for HF and highest for the HI. Enthalpy of dissociation will be easiest for HI and highest for the HF. pK means negative logarithm of K. So K is highest for HI, it will have lowest value of pK, see minus 10, and it is highest because it is the weakest acid among all of them. The order of melting boiling point is explained here. Okay. There is an exception, everyone. So I must not write maximum and high. This is where we have found that HI has higher melting point than fluorine, and boiling point will be higher for HF only because of the extensive hydrogen bonding. So this is something that we have to remember. We have to learn it directly. So reactivity towards oxygen we are talking about, and fluorine is mostly reactive with oxygen, and it forms two type of compound, OF2 and O2F2. So OF2, oxygen is present in positive 2 oxidation state. O2F2, it is in positive 1 oxidation state. O2F2 is similar to H2O2, hydrogen peroxide. It is similarly like that. There is no requirement of rote learning this data and all. This is something which we can use the chemical bonding, and we can predict out their order of bond angle, bond length data and all. O2F2 is very important to us because, so anyways, they are all thermally stable. They are named as oxygen fluoride because electronegativity of fluorine is greater than oxygen, and both are strong fluorinating agent. Whenever they are reacted with some substance, they convert them into their fluoride, such as O2F2 oxidizes plutonium to forming PuF6, which is plutonium hexafluoride. Right, guys? Next is, the reaction is used into removing plutonium from the spent nuclear fuel. So whatever the nuclear fuel is there where plutonium is present, plutonium reacts with fluorine forming PuF6, and PuF6 is removed out as a removal part, effluent. Chlorine, bromine and iodine, we are talking about their reactions with oxygen. They also form oxides, which are oxidation state ranges from +1 to 7, and these oxides are, let me tell you, like Cl2O, ClO, O2, Cl2O3, Cl2O5, Cl2O7, such type of oxide exist. Now you can check out their oxidation states. For oxides of iodine, the stability is more due to the greater polarization between the iodine and oxygen bond. Multiple bond formation between chlorine and oxygen takes place due to the availability of d orbitals, and this leads to the increase in the stability of chlorine oxide. And bromine lacks with both of the character, with the covalent character and polarizability, and also with the acceptance of the lone pair. So that is why bromine is actually least reactive towards the reactivity with oxygen and doesn't form very easily these compound. Then higher oxides of halogen more stable than the lower ones. Lower oxides are lesser stable, higher oxides are more stable. These type of basically atom, chlorine, bromine, iodine, these are very huge in size, very basically large in size. They can easily accommodate oxide ions or oxygen atoms across them, and that is what it has been discussed, that fluorine, oxygen only form some limited number of compound, but rest of them form multiple number of compounds. Talking about the oxides of chlorine, these are the oxides which exist. Please read these notes very importantly and carefully. I will share these notes on our Telegram channel. Please read these notes, very important notes are there. So because out of these only the question are gonna to come in your examination. So like chlorine oxide we are talking about, these type of oxides are there, and they are highly reactive and oxidizing agent, tends to explode. ClO2 is used as a bleaching agent for paper pulp industry, textiles and water treatments. Bromine oxide, Br2O, Br02 and Br2O3 exist, and the least stable halogen oxide actually, which is of bromine, and they only exist at the low temperature. They are highly powerful oxidizing agent because they dissociate themselves, releasing either bromine or oxygen as an oxidizing agent. Iodine oxides are insoluble solids and they decompose upon heating, and I2O5 is a very good oxidizing agent and used in the estimation of carbon monoxide. So I2O5 is actually used as a so anyways it reacts I2O5 reacts with carbon monoxide forming I2 and CO2. So that is why it is useful in detection or analytical chemistry of the carbon monoxide. Then halogen reacts with metal to form metal halide like bromide. Liquid, the ionic character of metal is this, definitely with most electronegative will be having the highest ionic character. And also with going down the group, the anionic size increases, more polarization brings more covalent character as per the Fazan rule. I can simply write this. This can be explained using Fazan rule. Fazan rule. If a metal exhibits more than one oxidation state, then the halide with higher oxidation state will be more covalent, because more positive charge over the halogen atom will give it more polarizing power. Some examples are SnCl2, SnCl4 is more covalent than SnCl2, SbCl5 more than this. This is what we know. Okay, metal like polarizing covalent character of a compound. Covalent character of a compound is directly proportional to the polarizing power of cation is directly proportional to the charge of cation. So higher is the charge of cation, higher is its covalent character in the compound. This is what the Fazan rule says. Next is anomalous behavior of fluorine. Fluorine being most smaller in size. Fluorine has the highest electronegativity among all the elements of modern periodic table, and also fluorine has the highest Z effective. It has some exceptional properties. What are those? It has high standard reduction potential, due to which it is very good oxidizing agent. Ionic and covalent radii are very smaller than the expected. Then abnormal behavior of fluorine is because of its smaller size, and we already have discussed about this part. Most of the reactions of fluorine are exothermic, because fluorine belongs to second period, and it is it forms bond with every even possible compound, every element, and releases energy with the bond formation. It forms only one oxo-acid, which is halogen acid, which is hypofluorous acid. This is HOF. This is the only halogen acid that it forms, oxo-acid actually. Next is HF is a liquid, and because of the strong hydrogen bonding, rest other are the gases only. Okay, this is the only difference we find. Reaction of which halogen with water is non-spontaneous, which does not react. This is iodine. So very simple to explain, and reactivity decreases down the group. Which of the following displaces bromine from the aqueous solution? Any one ion right above to it, which is Cl minus also, F minus also. So what do you think, which can replace, which can displace Br2 from aqueous solution containing bromide ion? Bromide ion can be replaced by the either Cl2 or by the F2. So Cl2 is correct answer. There comes another question. The correct statement: ClO2 is used as a bleaching agent. Maybe. Quantitative analysis we already have covered. These part we have covered. Cl2O explodes in ammonia when it is liberating, and I think all of them are correct. D. The correct order of thermal stability of hydrogen halide. HCl is HF is more stable, followed by HCl, Br and HI. HI is least stable because HI contains 1s and 5p or I guess 6p bonding, which is not a proper bonding. HI is least stable. Oh, wait, what is this here? HI is, no, this is incorrect. This is correct only. C. Why the maximum oxidation state of any element is exhibited in its oxides and fluoride? What do you think? Why does it happen? Why the maximum oxidation state of any element exists in its, and why HF is a liquid, other are gases. This is the very clear, because HF has what? Exceptional stronger hydrogen bonding that makes it different from the others. Now, why the maximum oxidation state of any element is exhibited? Because of their most electronegative elements are only two: fluorine with 4 and oxygen with 3.5 and chlorine with 3. This is how the electronegativity works there. So that is why most of the compound with maximum positive state will be either making with the fluorine or with oxygen, right? Next question, everyone. Among the following, which is the most oxidizing agent? Fluorine, because it's I told you it's E0 F2 to F minus is highest. Standard reaction potential is highest among all. Now, which among the following factor is most important in making fluorine the strongest oxidizing agent? So, bond dissociation energy is lowest, ionization enthalpy is not even required, not needed. Hydration enthalpy, I guess, because fluoride ion gaseous in water makes F minus aqueous. This is the energy is released. This energy is called as hydration energy. Highest hydration energy it has. HF is the highest boiling point among all because of the HF is highest boiling point, strong hydrogen bonding. Most reactive, see, this question appeared in 2015. So wherever you find the polar nature, that will become more reactive. ICl is the perfect answer, I plus Cl minus. Finally, we have come to group 18, and guys, we don't have too much time, so let me just continue from here. We have noble gases with us. Exactly the similar kind of electronic configuration will be seen, but this will be having a complete P6 configuration. So NS2, NP6, 3s2, 3p6, P6, P6, P6 like that. And wherever in between things are required, so use this general formula. General electronic configuration will become NS2, N minus 2, F14, N minus 1, D10 and NP6. Fully filled electronic configuration we got to need to write. Okay, this is called as fully filled electronic configuration. So their occurrence, they usually occur in the atmosphere, and all of the gases except radon and oganesson, these two are the man-made actually, and atmosphere contains around 1% of the volume of argon gas, which is the major constituent. Helium and neon are sometimes found in the mineral of radioactive origin, that is pitch blende is one of the example, pitch blende, monazite, clevetite. And the main commercial source of helium is the natural gas, which is methane. With that, helium is somewhere found. So these all are the resources of uranium. Xenon, radon are the rarest element in their group. Xenon and radon. Radon is obtained by the radioactive decay of radium, with radium going to radon and forming an alpha particle. Organozone has been synthetically produced with the collision of CF and Ca. So here they are, their chemical production. No need to rote learn these all, just take an idea and move forward. We will fastly go with the properties, and we will definitely finish them in time. Talking about their ionization enthalpy, dedicatedly, consistently decreases down the group. I'll sit and I'll convey this data. Atomic radii down the group, extra shell is added, increases, simply increases down the group. Electron gain enthalpy will definitely decrease moving down the group. Only second period element here is something exceptional we have seen with the other elements of p block. We found that electron affinity is higher for third period element than second one. Here neon is the highest one, so do remember this data. I am star marking this. The order is completely different. Order is entirely different. Helium has the what should I call it, lowest electron gain enthalpy, highest is for the neon, and then also decreases down the group. Their physical properties, they all are monoatomic gases: helium, neon, krypton, argon, xenon. They are colorless, tasteless, and they are odorless. They are very less soluble in water, very low melting and boiling point, because they have very lesser interaction, weak dispersion forces, or we also call them London forces. We also call them London forces, or we also call them induced dipole forces. Helium is unusual property of diffusion through most commonly used as laboratory materials such as rubber, glass or plastics. Okay, helium has this unusual property of diffusing through most of the common substances, and the density and melting point and boiling point increases down the group, because we know that their size increases moving down the group, and thus their various properties such as density, physical melting point increases. Which noble gas has the different valence shell electronic configuration? Only helium, because it has 1s2. Rest other have ns2, np6 configuration. Why intermolecular force is most responsible in allowing xenon to liquefy? Which intermolecular force allows xenon to liquefy? Because there are only two type of forces: induced dipole. I guess instantaneous will be the correct answer. Which one of the following noble gases is not found in atmosphere? Atmosphere doesn't include radon. Radon is actually prepared from radioactive reaction, I remember. Okay, then we have the inert gas which is abundantly found in atmosphere. What do you think out of these three, which is found very abundantly in the atmosphere? Argon 1%, nearly 1%. Which one of the following element is the lowest boiling point? Lowest will be helium. No, even H2, because why? Hydrogen is the smallest in size, no yaar? Yeah, this is where the controversy begins. This is the factual data, guys. Let me just get to know the lowest boiling point. Okay, boiling point of H2 and He. Let me check if it comes with the data. Okay, anyways, we must remember this thing. It's a good thing that we came across with this question, and correct answer should be helium. This is diatomic molecule. diatomic molecule has higher dispersion force higher dispersion force. Then we have some uses of these compound, and then we'll wind up the session, everyone. Uses of these compounds. Helium is non-inflammable gas, it's a lighter gas, and that's why we used it in the filling balloons of meteorological observations. The balloon which go higher and with the lower density of them, they goes upside. These are the helium balloons. Also used in gas cooled nuclear reactor. Its boiling point is very less, and that's why it is used as a cryogenic agent for carrying out the various experiments at low temperature. Then we have it's used in to produce the sustained powerful superconducting magnet, which form an essential part of NMR, which is NMRI systems for clinical diagnosis. Nuclear magnetic resonance, we call it NMR, and MRI is magnetic resonance imaging. Good. Neon are used in discharge tubes for fluorescent bulbs and advertisement glass display purposes. Neon bulbs are used in botanical garden and in greenhouses. Argon is widely used as an inert atmosphere to create with metallurgical processes. It's also used in laboratory for handling the substances which are air sensitive. Leave it here. Then some question was asked back in JEE Main 2013. Which of the following statement regarding helium is incorrect? It is used to produce sustainable powerful superconducting material, correct. It is used in cryogenic, correct. It is used to fill the balloons, correct. It is used as gas coolant in nuclear reactor. It is used to fill gas balloons instead of hydrogen because it is lighter. No. This is not lighter than hydrogen, but hydrogen is inflammable gas. Hydrogen balloons can get fire. Which noble gas is used for filling electrical bulbs? Neon, I guess. No, argon. Which noble gas is used for filling? Okay, neon is used for neon sign bulbs, and this purpose is different for neon. Argon is filled to give the inert atmosphere. And guys, that's it for the day. I think that is it. I think we have had enough, and so guys, you will be getting notes. I must write it. If you want to get the notes from our Telegram channel, you will find. Guys, you can connect me on Instagram @chemistry_wizard. So if you face any doubt, if you are having any doubt, do let me know. Otherwise, we are winding up this session. Next chapter, I am probably thinking of D block elements. You can suggest me what chapter you want on priority. Probably we'll think of D block elements, because right now, as you can see, that we are now mid of finishing the inorganic chemistry. So let us first complete our inorganic chemistry, and then we'll come to the remaining part of the chapters. I will continue organic chemistry right after finishing your inorganic chemistry. If you are facing any doubt, you can let me know. I can help you in moving from here. You can ask me anything if you are facing as a doubt. We can take a ask me anything for a 5-minute session. If anyone faces any doubt, do let me know. I can help you with the doubts. Sir, we need organic. Okay, Vishnu, don't worry, don't panic. I will bring organic chemistry very soon as possible. And I personally think that there are only a few chapters left in your syllabus, especially if we are talking about the inorganic chemistry. We have just one chapter left with us, that is D and F block, I guess, and then coordination maybe. So I got to check it first, then we'll let you know. Anyways, you post your doubts, everyone, and let's see. You post your doubts here and I'll respond to you guys. Then I'll wind up the session. Anyways, I'll bring organic next time. Don't worry, everyone. Don't worry. I'll bring organic chemistry next time. Okay. Chalo, bye bye, everyone. Take care. Good night. Bye bye. We'll see you soon in our next video. So, those who haven't liked the session, do like the session, everyone. Please do it on priority, and then we'll see. We'll connect in the next class.